Uh, no, you put it on recording, no? Okay. How do you get the screen here? Bum bum.
Yeah, so if you just tab out to PowerPoint and start the presentation from there, it should capture everything
This.
automatically.
Okay. Yeah. Okay, ladies and gentlemen. First, I'd like to introduce myself. Let me just see where. How can I switch to the other to the Word file?
Yeah, so if you just Windows key D.
Mm, okay, this one here. Sign in. Oops. Next. All right. Mm-mm. Okay. Test this way. Okay. Yeah. Ladies and gentlemen, then I'd like to welcome you to the intensive course on wastewater and wastewater treatment and the connection to chemical engineering. My name is Wolfgang Pfeiffer. I studied chemical engineering in the University of Karlsruhe. There I made my pre-diploma, and then I finished my studies, undergraduate studies, the Technical University in Munich. I made my diploma there. After that, I worked a year and a half in Mexico. I did different things there. I was operation manager in a paint company and later programmer for a business administration system for a small wholesale company that managed a wide variety of products. That was still the time when you chased every byte, and you had to point your um, pointer on the screen. Then you had to direct this all, and a 5 megabyte fixed disk was our big pride, and it was a 100K central CPU thing, and 4 people could work at it, and it was only Business Basic. It was long before Windows was invented, so that was a totally different time. That was only back in the 1980s. So from Mexico, I came back to Munich, where I was awarded a PhD and presenting my dissertation on sewage sludge digestion after working 5 years in the Institute of Sanitary Engineering of the University of Munich as a research assistant. With my PhD, I got a job in a family-owned M&E contractor. M&E is for mechanical and electrical equipment contractor, and we planned and made the mechanical and electrical installation of all the equipment in wastewater treatment plants and even some water purification plants. This company had about 200 employees, and we had annual sales of about 200 million German marks in 1987. That's when I worked there from 1987 to 1994. In 1992, the company was sold by the owner family to one of the major construction companies of Germany. It was Bilfinger and Berger. And as I did not want to work in a large public company, I looked for a new circus, and they looked for a new clown. And I succeeded in being appointed professor for chemical engineering, water purification, and wastewater treatment at the University of Applied Science in Wismar in 1995. Wismar just is in the former GDR, as a German Democratic Republic, or East Germany. It is just 50 kilometers beyond the former border, and it's in between the cities of Lübeck and Rostock. It's right on the shores of the Baltic Sea. It's an old Hansa town, and it's about 130 kilometers northeast of Hamburg, which you might have heard of. In 2023, I shall retire from my job after 27 years of teaching, more than 70 publications, 100 undergrad theses, and 2 PhD students. One is still Not done with his work entirely, but we'll hope for that. I worked at Wismar has a University of Applied Science, and since I started some years ago, at that it was all the universities of applied science were really known for being very close to the practical jobs, as working with companies also. And for doing that, I was able, in a small company owned by an institution, to do more than 10 million euro construction and consultant work, and earn by that an extra fee of about 1 million consultant fee over the 27 years. So that was kind of nice. Well, I didn't have all the money for me. I had to spend it for traveling. I had to spend it for students, and I had to spend a part of it. So about 1/3 or maybe 25% ended up in my pocket, and financed my vacation with my family. Well, universities of applied science offer professors a life of teaching and working still 1 day a week in their profession. That was a deal. I called always brush your teeth, not that you're not an academic teacher and get lost in science and publications, but that you really do some real work, what your students, when they graduate, also have to do when they find a job. No? And so it's close to the job, and we prepare the students to really know what they have to do when they get a job. My profession is plant planning, construction, commissioning, and optimization, and wastewater and sludge treatment mainly. I did a lot of jobs in industrial wastewater. I found this combination of teaching working especially rewarding. I liked it always. My work in engineering practice, and I experienced as enriching for my lectures, because it was easy to talk about my projects, which I will show you some next. So I hope I can meet also these expectations in this course. So let me just try to change to the other file. Yeah, I guess it works easy. Text is in German. I'm going to present you 2 or 3 different projects I did. The first one has to deal with hair cosmetics producer. It was a company Goldfill, which then was bought by Japanese company Kao. And that was done still when I was working in the M&E contractor close to Frankfurt. Then I will talk about the development of a very small and very cost-effective DAF, as a pressure. DAF is air flotation, dissolved air flotation plant. I will present that, and last but not least, I will present a project of planning and then constructing also a biological treatment of wastewater from a milk company with an SBR process. So here you see the wastewater from the hair cosmetic company, and here you see the effluent, and in the back you see the solid waste from the filter press, what we saved it. But you'll see this in a better picture later. What you see here is how everything started. This, however, is a little bit polished because it was on a trade fair where we presented this process of advanced oxidation with hydrogen peroxide and UV light. The combination of hydrogen, also if you treat hydrogen peroxide with UV light, you create OH radicals, and they have the highest oxidation potential so far known. So even a little bit better than ozone. You can create it from ozone, you can create it from hydrogen peroxide, you can create it with a combination of hydrogen peroxide and UV light, or hydrogen peroxide and iron salts. What you see here is, some of you should know this color. It is, the color is phenolphthalein. And we wanted to use this in this trade fair. We wanted to show the application for paper companies and threads, the dyeing of threads has to do with dyeing. And phenolphthalein, well, you all know when it's caustic, you have this nice purple color. and when it's acidic, it's free of any color. So those two little apparatus here are pH detectors, and of course we had to prove that in this way you don't see where the color is destroyed, that you still have an alkaline pH of 9, where you should see the color. So this phenolphthalein solution, just made out of caustic soda and a very dilute, and phenolphthalein was pumped through this UV reactor, and with this pump here was added hydrogen peroxide, and after passing the small reactor, the phenolphthalein color was destroyed by catalytic oxidation, what we call it, but it's a radical oxidation process. This is, this fits on a table. It's all very small. This is the dosing system. This is a pump that pumps the solution through the reactor. This is pH meters, like and all. This is a 300 or 500 milliliter beaker glass. You know this all from the lab. Okay, then the idea from this lab experiments, because when we went to this hair cosmetic company, they really wanted a DAF, and we were producers of DAF, dissolved air flotation units. But in Darmstadt, where the company was located, they had a stricter standard for verzeifbare Öle, verzeifbare Fett, also fats out of the edible side, where you can, it's not mineral oils and fats, but the normal natural fats and oils. And that was too low. We couldn't reach that with DAF, so we had to think something up. And just for playing around, because when you recall and you see this, you would not expect to get anything done with UV light treating this wastewater, which is thick in solids and color. So UV light is not going to penetrate very much through this wastewater. So just playing around, we used this unit, and my chemist in my laboratory, he developed this process. He said, yes, if you treat this for 3 hours, you get a result. And the color is changed to a sand color, as it gets a lot lighter, and the smell changes. I don't know what happens, but something happens. And if then after 3 hours, I treat it conventionally with ferrous chloride solution, lime, and flocculant, I get a clear water, and the sludge I get looks pretty nice. It should be dewaterable. So I said, okay, try this on 10 different wastewaters, because you have in an industrial company, hair cosmetics, they produce more shampoo, the other they have a hair fixer, and they have all kinds of different products. And they wouldn't give us the recipes, of course, of their products. It was their secret, of course, production secret. And even if they gave it to me, they work with more than 200 different chemicals. So what knowledge does it give to me if they give me a list of 200 chemicals in all kinds of combinations? What can I deduce from that? I can deduce nothing. So this is one of the bases of chemical engineering. It's a very experimental orientated engineering science. So you just have to experiment. You don't really know what happened, but then you see, and if it works, different combinations, then sometimes you have to say, okay, we found a way. We don't even know if it can be scaled up, and the upscale is really the core job of a chemical engineer. That's what I study, and that's what I did all my life, more or less. So the next thing is we built a pilot scale plant. What you see here in front is a UV reactor with 18 lamps of 1 meter, not one little lamp of 45 centimeters. It was the flow was always in chambers for 3 lamps, and there was chambers one after the other, so there was 6 chambers that would be flown through in series. We had a control panel here, and we had here a bunch of other chemicals we could add, because we also worked with different catalysts like ferrous chloride, and later we found out we had to work also a little bit with copper. We had to adjust the pH by acid and lime and sodium hydroxide solution, and of course we had to add our oxidant, the hydrogen peroxide. No? Okay, then at the end of the day, that's what a process engineer does. He makes process schemes. This was now the process schemes. You see here the first process scheme which we had here was chemical oxidation with UV, hydrogen peroxide and catalyst, then do a flocculation and do a slump conditioning. Well, if you do that to a plant, you have to say, well, the wastewater comes, normally I have to store it. So what kind of process do you have? Do you have a continuous process? Do you have a semi-continuous process? Do you have a batch process? Well, due to that, we didn't really know how this unit, the central unit, worked. We decided for a semi-continuous process. So we would always have an alternating equalization tank. And one day we would fill one tank. The next day we would empty it by treating it through the plant, and would fill the other tank, and alternating every day one tank, because this had to do that we had to the dosing, the pH, and what catalyst and how much catalyst we could try in the first batches, and whenever it ran, we knew that for this tank, this was the recipe for dosing the chemicals and the pH and the amount of hydrogen peroxide. And then the plant could run all day and all night and finish up the wastewater of this tank. And next morning you had to see if it was the same. Later it turned out, because the more experience you gained with the process, of course we had pretty much standard programs, and only a few days there was problems and you had to change the dosage. Where after this radical oxidation in this process, we had this flocculant tank. We had there 4 streets of this in parallel. We had 2 lanes of flocculation tanks. And then after the flocculation, it was also sometimes the sludge floated, sometimes it sedimentated. So what we did is we put a sensor for turbidity, and whenever it was turbid, it would go to the sludge treatment. Whenever it was transparent, it will go to a final filtration to get out the few flocks that were still in there, and then it was discharged. And with this process, we could meet the discharge limit. There's a lot of history about when you build such a plant, what happens. One day, they were already constructing this the thing in the civil construction was up to the this was all done, and they were just putting all the housings here, and then we made a last test, and we ended up purely in foam. No, it just foamed, and we couldn't control the process anymore. So we tried and we tried for 2 weeks, and we were just standing in foam. No? We went back to the lab scale. Also, when we started to get from the bench scale into the pilot scale, we started, and my chemist from the laboratory came back and said the process doesn't work. No, we have tried 100 liters or 300 liters, and after 5 hours we didn't see any difference with this oxidation process. So finally, I had to spend a weekend in the company, and said, because they were so frustrated, they wouldn't go back next Monday. So I went there and said, you have to get something done over the weekend. And so I started, because they said we refused to start only with 50 liters. They're just playing around in the kindergarten, no? Because the process will never be feasible then. So I went there. I started with 50 liters, and I got it, and something happened. And 50 liters was already a scale-up factor of 20 more. It was 20 times the wastewater on the UV light in comparison to what we did in the lab scale. So that was a pretty nice factor. So at the end of the weekend, I was with 300 liters, and I got it done. No? But just by altering the pH a little bit, altering the catalyst a little bit. So I came with my chemist and so on. We went over there, and I showed him, I can show you 300 liters, and then you get it, you optimize it. And at the end of the week, they were with 1 cubic meter. And we said that's good enough. That's what we can afford to build, no, and to make it, because they have to have a solution. And so finally, this is a plan for only 50 cubic meters a day. And I now have a company. They discharge. They have only 10 or 15 cubic meters a day. They also produce for Schwarzkopf, also make those pre-products, and they have to pay 275 euro per cubic meter for discharge. No? And so for them, this entire plant at the end was an investment of 12 million German marks at that time, because it was built in the 80s. At the end of the 80s. And the building was 6 million. The Technics inside was 3.5 million. 1.5 million was this installation, lights, toilets, because this is a social building. This is where the key process is. This is where the UV reactors and this AOP, as Advanced Oxidation Process units, are. Here is only, in this area, is only chemical tanks. On the floor, on the ground floor, on the first floor, it's all the dosing technologies, because there's 4 lanes of this. And this section is going down to the basement. In the basement, in this section, are the equalization tanks. And in the basement here, or in the ground floor going to the basement, are the flocculation tanks and the conditioning tanks for the sludge. You're going to see this, of course, and this is only the social tract. No? And so all the technology was just 3.5 million. The whole project was 12 million. Those guys gave out here 1.5 million for the gardening. No? So when I finally figured that out, I got so mad and said, "Shit! Now why didn't you offer for 5 million?" And we had so much trouble with that. And at that day, when we were just in the foam, no, and we couldn't get anything really done, no. So I had to write a letter to the company. We have what we did is, first I asked if I can get a wastewater of the same products only from last year. If they had, because I knew if you sell hair products or any products that are for human application, you normally have to store everything for at least 2 years. If there's anything comes, someone gets sick from that, you have to prove that you are not guilty, or that nothing of your product is doing that. So they had this, and we had to go in there at Sunday morning, 3 o'clock, when nobody was there. So we took one of these store-back samples, no, of the same products, and then we said, okay, we take your video equipment as well. We just lent that, no, and made a video of these old products and of the new products, and it was a huge difference. And with the old products, it worked, and with the new products, it didn't work. So I wrote a letter and said, okay, we have a problem. You change something with your products, and the CEO from that company just wrote our company, to my bosses, of course, a short letter. You better solve this problem. If not only your company is bankrupt, but your bank is also bankrupt. No, we'll sue you to the end of your life. No, and so we said, we have to discuss that. So that was also an experience you have as an engineer you might not expect. We came to this company. So they have, of course, a room where they present their hair stylings. And they have a stair, how do you say, a walkway or wherever. They were sitting on top of there. They had put some a small table and chairs from kindergarten in front of that. So we had to sit on those kindergarten chairs. No? And they were looking from top on us. No? Of course, we had a suit and tie and going there. And there was their CEO, and then there was all the heads of the departments, all in a very clean white laboratory suit, or whatever you. Laboratory code, no? And so then they presented one after the other. They hadn't changed anything, no? Well, they could tell us anything. And then at the very end, showed up someone in a leather jacket with sunglasses, no? Coming in, obviously not prepared. And he was also asked a question, what did we change? He said it's easier to tell what we didn't change. We changed all the tenside combinations. We introduced I guess it's, tensides that have an aliphatic and an hydrophilic end, no? And all this kind of stuff. So he was very proud of telling us what they all had changed. The other guys, 15 guys before, had said we haven't changed virtually nothing. No? Well, he wasn't obviously instructed. No? And so and then it was silence, well, really silence. Could hear a needle fall. And then it was like, when something crumbles, a building, no? At the end, without saying anything, always from the end, the guys left, no? And at the end was only left the CEO and our three sitting, the guilty people sitting on these kindergarten chairs. And then the CEO told me, well, Mr. Pfeiffer, what's going to cost me that now? I was, just 2.5 years in my job, no? What did you tell him?
I don't know. What do you say to that?
Well, I told him I want 250,000 marks, no? Because I thought that was a pretty outrageous thing. And what happened? This guy got out a checkbook and wrote me out a check for 250,000 marks. He gave it to me and he said, I don't ever want to hear anything from this again. He gave it to me, but he issued it to our company, but he gave it to me personally. Well, what do you do then? Well, I said to my two colleagues, I know something. There up there is a 2-star Michelin restaurant, and that's where we go now. That was the fanciest and most expensive dinner I ever had in my life. And then we went to the company. I gave them the bill for the lunch, and they looked at me as if I was coming from the moon. And they said, "Well, I have something else for you." And I gave them the 250,000 mark check, so they were relaxed then. No, they said, "Okay, we got to solve the problem now." And they really had to change back a lot of the products because it was itching the head skin. And after 4 weeks, they changed a little bit back. We changed our process a little bit, and we could commence our work. No? They, anyways, had to construct the thing. But that's something. That's what makes engineering life a little bit interesting. No?
So, can I ask you a question?
Yes.
Practical question. So, there's all this money floating around for this installation, but they couldn't afford parking spaces.
There's here.
Okay.
And this on the back side, this is solid waste management, no? And then behind it, they have a nice park. They have a little river flowing there. That's also the river, the receiving water, because the wastewater treatment plant is a little bit in this direction, maybe 2 kilometers. And they really had foaming before we installed this plant, foaming on the effluent.
So just out of curiosity, I mean, having worked in the chemical industry for a while, I know that there are, of course, very effective anti-foaming agents. What kind of material, what type of anti-foaming agent would you add to a wastewater effluent in this case?
You better don't. Because if your effluent in a wastewater treatment plant is foaming, you don't have a good cleaning result. So you're not going to meet the effluent criteria anyways, no? Because the foaming is going to come from something. No? So you just have to see. You have to do it. You should go to the root of the problem, because they make 50 cubic meters a day, and the wastewater treatment plant is probably treating a couple hundred cubic meters an hour. No? So you're not going to add there, and it's going to be very costly also, and it's not really solving the problem, because if you have a problem, you don't want it in the river.
Yeah.
You want to solve it, no? Okay, now to the technology. This is the same reactors as you saw in the pilot plant. We put here now 2 for one bigger reactor because we treated 3 cubic meter in one batch, and we had 4 lanes, so we had 8 of those reactors. And then comes all those nitty problems, no? Because in the real wastewater, you have some solids, you have some hairs, you have everything. So you have to have filters and pumps, and then you have the filters you have to control with pressure loss, as a differential pressure controls, and so on and so on. That makes the plant a little bit more complicated. So the P&I scheme was at the end was 8 DIN A0 pages, no, for the entire plant. So there was built a lot of stuff, no. This is the reactors now on the first floor. Below is below the reactors are the UV reactors. Then you have here. This is we had to spray it because of this is how we control the foam, because when you start the reaction of course it foams, so just by simply showering we were able to control it. The reactor had of course a 5 cubic meter volume, so it had about 2 cubic meter for foam. Okay, this is now ground, no, sorry. This is the ground floor. You see back here the reactors. This was for lime, and the lime, making lime milk station, which is also something a little bit complicated. This was ash from an incineration plant for giving the sludge a better structure. And the sludge really was used in a brick company for making clay bricks. This is where the sludge conditioning was. This was where the sedimentation was. Above where I'm standing here and making the picture is filter press, and behind me is just the different storage tanks for the chemicals, not for ferrous chloride, for hydrochloric acid, sodium hydroxide solution, and of course our nice little 30 cubic meter tank for hydrogen peroxide. No? That's temperature controlled, and the temperature control has a direct connection to the fire brigade department. No? So if that heats up, then they all come. Unfortunately, it never happened, as far as I know. This is a control room, and then it's a social building here. This floor actually had a price of 800 German marks per square meter. The Hyatt Hotel was built at the same time. They had only a floor for 750 German marks per square meter. And they later made here, because at that time it started that environmental was also something you wanted to show if you do investment in environmental. So they really presented their hairdressers here, and they put up with palms here, and this was why there was so nice a building with glasses and so on. I've never been in such a nice building ever again. Now, normally wastewater treatment plants are somewhere in the basement in the last corner. No? So that was here a nice experience. Okay, and this was at the end. This is wastewater. This is water. It doesn't only look clear. It has a COD of, I think, 200 or 300, and the fats, also soluble fats, were below 60. No? And this is a sludge cake that went to the brick company. No? It was it was from operation cost. It was okay. Investment was high. I think they I don't know what they did, but I think they are not using it anymore. They stopped it after 20 years. They changed. I don't know. I haven't been there. My son is now studying in Darmstadt. I've been in Darmstadt 2 times, but I not have made it out to the company. I kind of want to look what is with the plant, if it still exists or not. Okay, the second one is for pet food pre-products. This is basically meat that comes out of slaughterhouses or packing houses, and this is meat that is good for human consumption, as you could sell it, but you can't sell it because no one is going to buy it. No, it's intestinians.
Sorry, is this what we would call pink slime in the U.S., like the scraps off the bone that you treat with hydroxide?
That kind of stuff. No, what you can't really. It's good. You can sell it. This is also what they do, and in Germany, I think in the U.S. the same. There's a lot of stuff. It's not, when that pigs are exported to China. It's not that all the pig is exported in the pig meat. It's only parts of the pigs, because they eat a lot more intestines and things, feet and head, what we are not keen on. That stuff goes. So it's of every pig apart. 30% of the pig is always sold to Asian countries. And because in Germany and the United States and I think in almost Europe, we want the cutlets, we want the steaks, we want this kind of stuff, we want the ham, and all the rest which we don't want, that goes to different countries. No, and this makes our meat so cheap. Well, probably things have to change that anyways. This might be even a product prime because then later they just freeze it and these frozen plates they send to the pet food companies, no? And they just can it up and sell it, no? And when the stuff from slaughterhouse comes in the truck, you of course have here blood water and when you have those boxes you have to clean, and sometimes from chicken stuff, or they sometimes get even what you're sending the girls to here from fish stuff, because they make it also for what's now going also the animals you make coats of nerds. They have a lot of with COVID they had to kill all the nerds in Denmark. It's those little animals. Minks, yeah. Okay, sorry, minks. Yeah, you're right. This guy who operated this plant, they used to have mink farms also, and they said you can see anything of the process here. When I asked him, he said, because there's just 5 or 6 producers of that kind of stuff, and Chappie and all those big are not going to buy from anybody else because they know they estimate our know-how, and meanwhile by operating biogas plants, I also learned that you got to have trace metals you have to add to a biogas plant if you operate it only on energy plants. In sewage sludge and in manure, you don't have any problems. You have all those trace elements. But if you work with only with energy crops, you have a problem. You have to add that. Also, which I was surprised, when you work with food. As we built one biogas plant recently for a guy who cleans the inside of trucks, which transport food on the road. No, milk, chocolate, oils, and all this kind of stuff. And they have to go to a cleaning. They get cleaned, and the wastewater, and he pre-cleans them. And the pre-cleaning has a COD of about 100. And so we sent that to a biogas plant, and there also we learned we had to add trace elements, and it's the same trace elements that you also add. And this I didn't know because I'm not from the agriculture. The farmers also use the same products more or less for their cows, for their horses, and for everything. You need those trace elements that they have nice shiny. Animal skins on and all this kind of stuff, no? And so they said they will only trust people that have experience with that.
Just out of curiosity, with respect to the trace elements, do you guys happen to go to the bother of identifying which trace elements you actually need to add, or just perhaps throw the kitchen sink at it?
I know, sometimes it's good if you know someone who knows, no? And for me, it's Dr. Limdorfer, because he is from Austria and he made his PhD on trace elements. I have his PhD thesis, and I looked into it, and he has found out what are the limits, and he works for the Schaumann Company. Schaumann Company, I think, was found in 1907 or whatsoever. They have over 100 years of experience, and they sold this always to farmers, and now they are the leading. There's 2 or 3 suppliers which we have in Germany that send this micronutrients and trace element mixtures to biogas plants. No, with him, I just suggest that to my clients, and that's it. No, so they have one source, they can buy it, and he helps me when I make my pilot studies and all this kind of stuff. No? Okay, this is a wastewater that they have. And this is what it looks like after you add iron, because blood you can really flocculate very easy with iron salt and keep the pH around neutral. And then again, I send a student there because this is also an experiment that we show our students. This is our DEF unit. We just make our, we just have water and we press air into it by bubbling, and then we have a valve where we can adjust the pressure. Then it opens. So if we adjust it 4 bar, we blow it up with air, compressed air, and bubble the water through. It's more or less the same thing what you do for if you make carbonized water at home, no? And you have your carbon dioxide bottle and kind of the same technology. And then we underlay this water, with pressure saturated, air saturated water, and you'll find out the bubbles come out very fine. It looks like, and in English it's also called milky water. It looks a little bit like milk. This is difficult to describe. If you've ever seen it, you know what I'm talking about. Sometimes you have it out of tap water. Yeah. This is because when they have too much when you have pressure in the pipes, when they don't have a membrane between the buffer tanks, then you will have the same process that oxygen loses. And when you get it out of your water and you have too much pressure on your tap, then you'll find you have this milky water. No. No. Okay, when you underlay this water, maybe 25, 50% at the end of and you wait a little while, this is what you get. No? If you watch carefully, it's a little bit high. It's difficult to see, no? But it's about 50% what we added here. And this is DAF process. It's standard. You can design it more or less from the writing table, no? From the desk. Okay, this again is a process scheme, a little bit more now can elements. We have here an equalization tank with sedimentation of the Coraz stuff. This is what you've seen here. You don't want to have this in your plan, no? So you just have this sedimented. Then from here you have a pumping station. The pumping station goes into the big equalization tank because they had only 15 to 20 cubic an hour a day, and so they just run the plant for 4 hours a day. No? So they just do their day's work, and when they are done, they just press a button or press a button when the tank is more or less a little bit filled. Or it might be even that we have I think we have automized when it's filled, it starts itself, and you can start it, of course, manually when you finish your work to empty the tank for the next day. No? Then you have a Accenter pump here, kind of a screw pump, monopump. That is for getting controlled flow. Because the flow is proportional to the revolutions the pump has. Then we add the ferrous chloride, then we adjust the pH to neutral again, and then we add our flocculant in the flocculation tank. And from the flocculation tank, you go into this DAF unit, which I will describe a little bit because it's the heart of it. And then you have to get the sludge into a sludge tank. And this sludge is sucked by a farmer, and he puts it on his fields, no? Or he puts it in his biogas plant, and out of the biogas plants he puts it on the field, because this, of course, this is a lot of fat in here. This is really nice for biogas. The problem was a friend of mine, we made the consulting, and then we made a tender. And then another friend of us, he has an NME contractor company. There's about anywhere between 20 and 50 people he employs, sometimes more, sometimes less, depends on how the market is. When there was a big biogas wave, he had up to 60 people, and now after the biogas broke down, he went again back to about 30 people. And he got into the tender and offered the company I used to work for. They offered 387,000 marks for this plant. The more aggressive companies on the market like Huber and Nieuwhuis from Holland, they offered 208,000. That was a realistic price, and our friend offered 200,019. And later they lowered him in negotiations to 190,000 flat. No? And then he went and then he asked me, well, how do you construct this thing? Then he looked at what the competitors did, and then he came back and said, okay, I can't. There's no way I can construct it what they do. I cannot make it at that price I offered. We have to do something different. So we started at the porch of my house. We started to make a float DEF because he has never seen a DEF. So we made a small DEF on the porch of my house was an IBC tank, and playing around there. And giving different ideas. And then I had a very good student. He did in his bachelor thesis, at that time was still a diploma thesis, he had 3 different projects. One of them was to help us with this DEF unit. So what we did, we bought a PE plastic tank, already with a cone inside. That cost us, I think, €3,500. Wasn't really expensive, no, because it wasn't big. It was like 2 meter in diameter, 250 in height or something. And then the real thing was how to get the sludge away. So we just put here a screw, a conveyor screw, and we just in a pipe, and we just opened the pipe on top of it. And then what we did, it was windshield wipers from trucks. We put this construction here that was turned around. There was just one motor on top of it, turning all this, what you see here in black, turning it around. And this was, because this was the inflow here, and we had also for static, and we had 2 holes here, so the inflow could always work in this little chamber. This was isolated with O-rings. And then in this main column, we entered here the wastewater, and from the bottom, we entered through, we just put it on a block, and through the block, we pumped in the pressurized water, and the wastewater would go out here through these ones. They were a little bit in an angle, so the wastewater would be released first, and the pressure water would follow. No, so the pressure water would then be under the flocks, go under the flocks, put the wastewater up here, and the sludge was being was by the windshield wiper was put into this screw conveyor. The screw conveyor you don't need to control. It can run full of sludge or it can run full of air, no, because it moves very slow. So you have almost no friction, and the wastewater would be collected underneath here, go into this chamber. And this chamber had an overflow where the effluent was, and this was the overflow here, and also from this small connection here was going to supply the pressurized water. No? Okay, now in concrete you see this here. This was a construction. All this material is standard from a company called G&F. It costs us, I think, €500. All this you can just. This is another all the steel work and the motor is maybe €2,000, and this really was a little bit eccentric. These the sludge collector, the conveyor. Spiral, and this was the windshield wipers from the trucks. No, and this would be turning around here. Here you see the 2 different distributors. Let me see if I have anything else here. The hardest work was for the poor guy who had to weld all those half-cut plastic pipes here in this cone, no? Because this is welding there, and sitting in a cone is not really very comfortable, to be honest. And this was a pressurized water going to the central block. This is where the inflow comes into this connector, and this was blind flanged here, so the water could just get out through those holes here, and the pressurized water would go out through these holes, which you see here. So the whole thing did just cost €35,000, and the project was very profitable. Because the standard solution is about what the other suppliers, if you just buy the naked flotainer of flotation equipment, you're with 150 to 180,000 euro, and to reduce that to 35, that left a little bit money for everybody. You know? This is a pump that is a 2-phase pump. And that is where you mix water and air and compress it to 4 bars. No? This is where the air is suction and the water comes. I don't really, I don't know if this is this might be the inflow, and this might be the air connection somewhere here. At least that's from Kiel and Edua pump. No? Okay, this was the second project which we did, and the third one is this dairy company here. This dairy company is also something very important. Here's the building for the production building and administration building, and everything, and trucks can run around the building. Like on the far side they unload the raw milk, and on this side is where these trucks load the products. No, they make fresh products, also yogurts, milk mixed drinks of all kinds, and drink milk. This was only a building left over for storage, and on half of the buildings was only milk cans. Old milk cans were stored there. This is for electricity house, and in this little area far be here, that's what I choose for putting the wastewater treatment plant, because it's very important. If you don't see a wastewater treatment plant, it doesn't smell. If you see a wastewater treatment plant, neighbors will always say it smells. No, because they associate that. They will, if they don't see it, and we never got a complaint here. No? So this is one also of the important things. Now, if people don't see your environmental units, they don't have any problems with it. So this was the area where you come, where you have to construct this. Then you find, of course, a power cable where you can use it. So you have to change a power cable to a different location. Then you come in the building. There was a milk cans here, so we cleaned out the milk cans, and I choose this to be my operation building. Integrated that. That was, of course, very cost effective. Just putting, a few walls, putting a wooden roof on it, and put the milk cans on top of the wooden roof, and everything was in order again. Then we had here. I wouldn't ever do that again. Make underground constructions in an operation building. It's a little bit dangerous. Not really, because it's very small volumes, but you can generate explosive gases, of course, or toxic gases. No, it's better to make it outside. No, that wasn't really a good idea. I got that probably one of the things I didn't do a very good job here. Then we integrated. This is a sludge concentrator. This is a flocculation tank here. It's on a rotary sieve. It rotates and it's flat, and the sludge is drained on this screen, and then is scraped off and comes off on this side here and is pumped away. No? This is the two SBR tanks. An SBR process is that you have the different phases. What we are going to talk about on Friday, about biophosphorus removal, denitrification, nitrification, sedimentation for separating the activated sludge from the treated wastewater, is done just in one tank, and it's done on a time scale. You have the two options. You do it for each unit you have a different tank. Then you do it all time-wise parallel, but in different tanks, or you do it in one tank, and you separate it by time and with the different phases, time phases. Okay, this is when it's fully equipped here. This is the influent. No, this is the influent here. And it either goes to an equalization tank, or it goes to an emergency tank. And this is a pump that pumps it back from the emergency tank in the inflow. It's whenever the wastewater is getting a critical composition, pH, temperature, concentration, then you just can pump it in an emergency. And because if it has a critical, an unusual composition, something has happened. No? Maybe they lost some acid or base, or some milk tank, they lost a couple cubic meters of milk or cream, and then you can just store this in an emergency tank and just pump it with, a small pumping rate into the wastewater, because then, especially if the wastewater is just not very concentrate at that time, and then you can dispose of those hazardous wastewaters, because the components in there are not different. It's just a concentration. No? If you have different components, of course, you have to think about different ways. And this is the effluent side from the two SBRs, and this is all where the control meters are. This is IDM, as an inductive flow meter, and then you have pH, turbidity, and temperature, and conductivity. That's standard. No? This is for sludge treatment. Behind my back is the control department. Behind that is where the blowers are. This was also kind of a nice idea. We had, for winter, we took the ventilators from the blowers, because the blowers produce heat. So we heated this room with the ventilation of the blower room. And in summer, we just inverted the blower. The blower was in this pipe here, and then a pipe which was going through the control room, and then you would get fresh air here through, and just blow out the hot air, which you didn't want in the summer in this room, outside, not just by inverting them. It was a smart idea because, of course, in this old storage bin we had no heating, so we didn't have to install any heating for the winter, no? Because the blowers produce sufficient heat for heating the room as a waste heat. No? Okay, this is what the milk water loses. This is the equalization tank. This is the two feed tanks for the SBR process. This is a mixer. And you can just, you have to go with an anchor and grab them, and then you can tow them out by those, by those, how do you say, those pipes where they are guided, not guiding pipes. This is oxygen or pH meter. This is an oxygen pH meter, because this is the equalization tank here. And this is the aeration tank. This is where you see the activated sludge. And this is then dissolved oxygen on DO meter, dissolved oxygen concentrations. And you see in those things that it's very good flocculating, because then you see those clear water traces there. No? That separates nicely. And this is, well, when it's aerating in the aeration phase. No? There's a fine bubble aeration over the ground floor distributed. Okay, that's a little bit introduction what I've been doing, and lately we had a couple breweries we had to consult. Nice job, no, we love that. I still have some jobs in milk industry. Right now, mostly was a Bavarian milk industry, and getting their flotation sludge discharge. Then we're going to build a 4.2 megawatt biogas plant there, in order to process their permeate melasse from the lactose production side product and the flotation sludge, and mostly also to become independent of the waste waste disposal companies, because they just eat you up, no? As they ask for 55 euros per ton for flotation sludge, and right now we're hauling that to the next sewage treatment plant, and for this transport we just pay 18, and we're finding a new transport for 11 euro. No? So the entire costs go down from 1.1 million a year, because it was 20,000 tons at that place, to maybe a couple 100,000. No? So that's giving it's better giving the money to the farmers than giving it to the solid waste disposal companies. No? And also this 4.2 megawatt, we can, because right now all the steam furnaces run on natural gas, and we can substitute about almost 90% of the natural gas by biogas. No? So that's also a contribution to climate protection, because we're talking about 700 cubic meters of biogas an hour. No? And that's some tons of. Okay, any questions, anything of this here? Or?
Actually, I have a question about biogas. I'm a little bit familiar with what the UK is doing with respect to biogas.
Mm-hmm.
How they've got kind of like this sort of grid network laid all over the country, where small biogas plants can basically pump their biogas and What's it like in Germany right now?
It started with Germany was one of the first countries to really make seriously renewable energy, how to say it, renewable energy law or no, that was implanted, and then it just blew up. And biogas plants, I think we have now, there was maybe 1,000, and now we have 10,000 biogas plants, and we have some pretty big ones. No? And but they got only this law was only for it gives you only the support for 20 years, and now it starts at the 20 years for most of the plants are over. And now and this is really this is the same for the windmills which we have in Germany, and it's kind of really rare. I don't know what's going to happen in the windmills, no, because I have a friend. They have a park of I think 11 windmills with each 2.5 megawatt, and they're probably going to tear them down and sell them to Turkey or China, no, because they offer them just 3 cents per kilowatt hour, and they need 5.5 cents, no, and they used to get 16 cents. That was, of course, but of course, these plants were pretty expensive when you build them. But now they are, now to keep them up, you can live with 5.5, 6 cents would be fine, no? And so it's really, I don't understand. Nobody talks in politics about it. None of the parties, not even the Green Party. This is a little bit my problem with the Green Party. I expected them to at least say what's going to happen to all this installation that are made. The same which is for the windmills. There's no solution for the biogas plants. Due to the bill on the CO2 payment. It was 25 euro per ton of CO2, which is going to rise later to 50, and I don't know where, which is, I think, a good idea. It's now the biomethane is a product you can sell, but of course you need for making it halfway feasible to convert biogas to biomethane, you need about 400 cubic meters an hour to production. No. So all the things which you operate with a cogeneration, this is probably going to die. There was one master thesis of a guy. He was the Stadtwerke, the utility company from our capital of Mecklenburg-Pomerania, Schwerin. They have a biogas plant. I don't know how big it is really. I think it's in the megawatt area, 2 or anywhere between 2 and 4 megawatt or something, and they operate with energy crops. It runs in 5 or 7 years. It goes out of these 20 years, and they have now tested if they can make with current, also if they can produce hydrogen out of wind energy, and then convert the CO2 of the biogas into methane by separate it and then have a catalytic methanization and then sell the biomethane. That seems to be right now alkaline hydrolysis and catalytic methanization seems to be right now the most feasible approach to that. No? Of course, you need a certain magnitude of a biogas plant. You can't start that with 100 kilowatt or 500 kilowatt biogas plants. No, for them the future is a little bit hard. No? You can of course rebuild this biogas plant when you can substitute methane on site, or when you with biogas without treating the biogas, which we did in the case of this. This company where they cleans the inside of the trucks. That gets a refinancing of about 6-7 years, only from the saving on the gas and only from the energy side, no, by substituting the natural gas. And if you would have to discharge this, they would charge them about 35 euro a ton, no, this other brewery. They have just very small amount. They just have maybe a cubic meter a day. There we have to pay that about 35 euro per ton of wastewater with about 100 grams of COD per cubic meter. That's transport and all this kind of stuff, and they have to sell the energy out of their biogas plant. That's not that feasible. So I think the biogas plants for crop plants, it's anyways it is an intermediate technology. It's going to disappear. For waste from food plants, I think there's going to be a bunch of anaerobic treatment plants or digesters. That's going to come because when energy prices rise, that becomes more and more valuable. So they're not going to give it away anymore. They're going to use it for optimizing their own CO2 balance, makes them look good, and it's feasible. So they are going to do that, no? Increasingly. This is what's going to happen in Germany on the biogas side, and other waste materials which you can use. No?
In terms of like with biogas plants, I mean, in terms of like safety of operation, I mean, obviously the partial pressure of hydrogen is probably going to be fairly high. Well, what does it look like from like a regulatory and monitoring standpoint, though?
Hydrogen? We hardly have any hydrogen. We don't measure it really. This is another problem. There's this Blue Sensor company. They have supposedly a hydrogen as a hydrogen detector. This is what I want to try, because hydrogen detector for having high concentrated wastewater. If you have only carbohydrates, you can run it through a USB reactor, IC as integrated circuit or whatever. Those optimized USB reactors. But then you need to control the process a little bit if you have varying substrate concentration and composition. If you have a standard, just one factory like a potato company, so you can just run it without controlling it, that works. But if you have more modifying, or you combine more 2 or 3 companies, then you have to look at the hydrogen in order to control your acidification, all this kind of stuff. That the one side, and the other side you would know more about the hydrogen. Up to now, if you just give it to a furnace, and you have just low hydrogen concentrations, and they're never going to be the explosive range, and so that's no problem really. I have not heard of any problems in cogenerators so far. And of course, they check the VOP index. They check all those indexes when you go into the public gas RAD. No, when you mix it with natural gas, you have to meet all those criteria. No? And they are monitored. No? So what is this is the competition for this. I think all those biogas plants for the food industry are going to come, because up to now, like in one big dairy plant in Germany, in Lempertshausen, or what it's called, Lempertsheim, in Saxonia, Miller's company they have installed an ethanol plant, but it doesn't run very well. In sugar companies, that ethanol plants are working well, and ethanol gives you a higher margin than biogas. They also have biogas plants. That's more, and in the sugar plants, that's more for all the other waste. When you have, from pressing the press cake, from the beet sugar and the stuff that you get out when you get the proteins out of the sugar water, all that stuff goes into the methane plant. But the molasses, and which almost pure sugar, that goes into the ethanol plant. No? So the pure stuff you can upgrade, and of course, what you want to do, the plastic production is also going to be a competition for biogas, because biogas it's generally going to be a transitioned technology as long as we need. Methane. The good thing about methane is we have all the infrastructure. We don't have a hydrogen infrastructure. So I think for the next 50 years, hydrogen is not going to be. It's just going to be. It's going to start like biogas started. We have, I think, one train that runs on hydrogen in Germany, but that's because it's very close to a company that's producing chlorine. No. They produce this. It's It's this American company. It's not DuPont, but it's the other chemical company, Dow Industries. No, as Dow Industries is producing chlorine in a company close to Hamburg, out of salt water from or backwater from the Elbe, and they make this alkaline hydrolysis, and of course they have a lot of hydrogen. No? And they are happy that they can sell it to the train company that runs the trains from more or less almost their works up to Bremen and forth and back. No? So they can regularly fill it. No? And this is how it's going to start. When you have local things and you can do that, the next thing that's going to come is Remondis, is a big waste company. They have one biogas plant. They make now the biogas they use for fueling their solid waste trucks, because nobody wants diesel anymore in the cities, no? And so they but gas is no diesel, no? So same motors. I don't know if it's that much better on nitrogen oxide on NOx, but whatever. No? So they really start doing that, buying biogas plants for fueling their trucks, so they can say we don't have diesel trucks, we have biogas trucks, climate neutral, and so we are the best and nicest people to haul away your garbage. This is what they really are focusing a little bit on. So this is a few things that's going to happen. No? But before hydrogen, you can convert hydrogen into methane quite easily, biologically or with catalytic processes. And I think that's going to be the intermediate future for the next 30 to 50 years, whatever, because the energy cells that work on hydrogen have not really advanced that much that they are so advantageous right now. They haven't really, I don't know, depends, no? Okay. Now this is so you see my work environment. What I've prepared for you guys. Did you forward that? You can forward that. Oh, okay. So you might have read it. It's a little, because I didn't know what people I face here, and probably everybody of you has nothing in mind but going on a wastewater treatment plant. Now, if they would have told me that when I was a student, or said you guys are crazy, no? Ending up at a wastewater treatment plant, I really find it's kind of challenging, because in the morning you're in a bakery company, at midday you might be in an automobile company, and at night, if you're lucky, you're in a brewery company doing your job there. So, because everybody is working with water, and if you work with water, you have wastewater, no? So, and it's probably the product that's more than anything else moved in all companies, no? There's only a very few companies that move anything else, but or any other chemical more than water, no? So it's really, and it's for a process engineer, it's kind of interesting to come to all those different companies which do different things, and they all have to disclose much of their production. That's kind of interesting. To see how they produce and what they produce, because you cannot build, and normally they don't look at the wastewater. I also once had to do something in a huge, pretty big bread company. They make about, I think, 9,000 tons of bread a month or something. No? So it's all good for all the north of Germany, more or less. This is golden toast, and I think they do a lot of that stuff. And when the company was built, the industrial planners, they to the wastewater treatment company, they said, we just going to discharge 128 PE. PE is for population equivalent, as is for people. No, that's one PE discharges 120 grams of COD. Well, when they were in operation, the discharge was 12,800 or something around that. It was a factor of 100. They were, misjudging their wastewater discharge. Okay, then we found something, because looking at their process, I found out that they dumped about 100,000 euro a year of raw materials unnecessarily in the wastewater. It was very simple. They had a tank where they were mixing water with flour and all those other ingredients which make up the bread cake, no? And this preparation of this raw material for the bread, or the Teig, was ein Teig? Dough? Dough, no? Are you German also? Or? Oh, you're good. Oh, okay. Yeah? Teig. Dough. Oh, okay. The dough is fed then in a equalization tank, of course, and from the equalization tank, the bakery conveyor takes it away. No, it's pressed in its form, put on a conveyor, and then it's just heated, and that's all you do for this bread. No, then it's cut and packed. No. And of course, the production of the dough is a little bit faster than the takeout from the into the baking conveyor, because the baking conveyor should run and run and run and not being stopped. No, so at times you have, of course, to stop the preparation of dough. Now with this kind of dough, it is when you stop it. They stop the filling of the preparation tank, and they shut a valve in between the preparation tank and the equalization tank. And when the preparation tank was standing too long because the dough is expanding, then it ran over. So they programmed, and some night session, I don't know how they did that idea. They just made a pipe to empty the preparation tank into the sewer. And whenever the stop was too long, so that the preparation tank wouldn't run over, the tank was emptied, and this is a sewer. No? So I said, "Are you guys nuts? No? Why don't you just leave this goddamn valve between the preparation tank and the storage tank open, and just when it still runs over, you just lower the stop." So you don't have to do that. So they reprogrammed it, and because we had an experimental wastewater treatment plant to find out how much of the wastewater because we got wastewater samples, we analyzed them, we looked at them, and there was sedimentable pollutants in there. So after sedimentation, the pollution was reduced by 60-70%. So we said. And how much sludge do we have to empty, and what kind of sludge? What is its viscosity? Does it cling? Or how can you pump it away? Or do you have to use screw conveyors? Or how do you have to empty that, and what happens with it? Then we put just a pilot, simple, a sedimentation pilot tank, pumped it away with an extender pump into a storage pump, and just looked at what would happen. We found out it works without problems, but close without problems. Because after the first week, I think, after 3 days, I came over, and everything of our thing was full of sludge, and really only like dough, not like exactly dough. All the pipes, we went home, put on the pipes, pressure was 5, 6, or up to 10 bar water, and then it came out like a sausage. No? It was pure dough and was not wastewater anymore. Well, then from the utility company, I heard, okay, yeah, we had on Wednesday or on Tuesday, we had this problem. We had to also clean all the sewer system. That costs always like 20,000 euro when cleaning. So that was the first time I went into the production and said, I want to see this. Where does this stuff come from? Okay, then they showed me, and they had 2 compartments where they were cleaning the dough manually from equipment. No? And they said, no, they are supposed to put it in a container, and that goes solid waste and goes to pig food or whatever, no? Pig fodder. And then I said, okay, I've been a student, and during night shift, I know what I do, no? Schlauch, what's das noch here? The hose, the water hose is my brush, no? I hose anything into the sewer at night shift when nobody's controlling, no? And this is how it happens, obviously, no? that then this dough accumulates in the sewer, and sometimes it's all closed. No, so I said, okay, we're going to put a video camera there. No, so the boss from this. He's not CEO of the company, but he's the man in charge of this production side. No? He said, okay, you discuss that with the labor people. No? And I said, yes, I have no problem. So I went. He announced it, and when I came into this room, 7 or 8 people from the labor union people, no, and they didn't eat me right away. They gave me a little chance, no. So I told them, I said, yeah, we need that. No, you're going to have the problems. Are you going to pay for it? Who's going to pay for it? They said, no, we don't want any videos here. And I said, well, who told you I'm going to connect it? I said, I told you I'm just going to put a camera. And if nothing happens anymore, we don't need to connect it. And to my knowledge, it's still not connected. No? Because it didn't happen anymore. So I said, okay, that's what we wanted. And that's what we easily agreed upon. They said, okay, you're going to put a camera, you don't connect it? I said, if you don't tell anybody, no? Because if you don't tell anybody, it might work, no? And we just tell anybody it's watched now, no? And we agree on that, and that solved the problem, no? That was one thing. And so from then on, they never had again to clean the sewer system. And then that day, they reprogrammed it. We measured that usually we had a certain quantity of sludge every day on average. And from that day on, we just set half of the sludge. So the pollution to the sewage plant was reduced from about 12 to 14,000 PE to 7,000 PE. And then we put the sedimentation tank. We just put a sedimentation tank. Originally, the wastewater consultant because this company had several bread factories in all over Germany, and so we normally all our wastewater is done by this consulting office from Aachen. I know this consulting office. It's a very good consulting office. And then this guy flew in, and he said, "Okay, I don't know what I'm going to do here." And he had a concept which was, with how do you say, with as very safe. No, it was Gürtel is here. This one here, but yeah, what do you have? Belt, genau. With belt, then you have this one. Men have some belt, suspenders, and chain. No? So safe at the end of that's what this is our saying in Germany. No? Belt, suspenders, and chain. So that's but the cost was about 600,000 euro then. No? So I believe that, but I don't know if we need it or not. Well, we ended up putting just a tank, and then the utility comes every 14 days. And they just let up the clean water because we have the sedimentation phase, the flotation plant. So they let up 2 or 3 cubic meters, and then they mix it forth them back in order to the scum, to destroy the scum, the top layer, and then they pump it in and drive it away to their digester, and they get nice gas. No? This is a company. I'm not. Before when I became professor, when I presented myself in Wismar, or was invited to present myself, the first thing I did is before I went to the university, I went to the sewage treatment plant. No? And I drank a coffee with the manager of the sewage treatment plant because I thought if I don't get along with him, I can't go there because I want my laboratory on the sewage treatment plant. Okay, then I was appointed professor, and then one day the rector of our university and the chancellor came and said, "Hey, Professor Pfeiffer, we're going to build you a nice wastewater treatment plant on campus where we're going to treat the campus wastewater for you." And I said, "Okay, you can build that. And I swear I'm not going to ever put a foot in this wastewater treatment plant." They were kind of, a little bit surprised. No? And I said, "Hey, I'm professor. I'm not operating a sewage treatment plant. No? My laboratory is going to be on the sewage treatment plant because there I have every media I need to experiment, and there they take me serious. I'm not going to operate here. In summer, no students. In winter, there I just get urine. I can't work here. No, that's nothing. Nothing. That's for playing around and not for serious people. No, okay." My laboratory is on the sewage treatment plant. Wasn't easy, no? because they told me it wasn't possible, and I said, okay, we'll get it done. No? And nobody wanted it, but I had to talk to the prime minister of our state, and finally I got it done. No, with the help of a few other people that thought it was a good idea. No? But it wasn't easy, but finally we got it done, and I'm happy with it now. No? We moved one sedimentation tank a little bit closer together, so I got my 400 square meter for my laboratory. Well, lost a little bit the thread. Where did we get from? Bread, yeah. And this is why you have to look into the production, no? And you can save there just any amount of money, and why you have to look this co-work of experimental work and design, no? That really makes it, no? And the other one, then we in Grevesmühlen is where they haul this was this manager of that utility company. He once got an approach. They wanted to make biodiesel out of the sewer waste from fat as grit traps. And it ended up that most of the waste from the grit traps ended up for co-digestion. And those guys that wanted to make biodiesel, they got into jail because of subvention fraud, you know? Because they took money and they never produced biodiesel, really. You know? I don't know what it wasn't that bad, but they were pretty well fined, and they had to go into for a certain time. They went into inspection jail, or however you call it, before the trial. No? But due to that, we started with co-digestion, and when he started, he said, I don't know if I can do it or not. I said, I have pilot scale digesters, we can do that. We just start with the pilot plants first, and we just give twice the amount of co-digestion or co-substrate into the pilot scale digester, and then if he doesn't have any problems, we're not going to have any problems in the full-scale plants. And that's what we did for over 2 years. And so we got from different sources. And we started, when we started the digester, they had 2 digesters of 900 cubic meters, a 45,000 PE plant for wastewater, and about 100,000 for sludge, because they take sludge from different other plants that are part of the utility company. And they had 2 co-generators with each 50 kilowatt. Today they have those don't exist anymore. Then we built one for 125. Then we built one for 250. Those exist no more any either. Then we built one for 335. That's still in operation. And now we built one for 807. So we operate now the 2 ones, 350 and 800. So we're just above 1 megawatt. So we supply all the energy for our plant, for the wastewater plant, and for all pumping stations within a circle of 4 kilometers. Because further we are not allowed to do that, and we have 97% of self-sufficiency. Not only on the plant, everything on the plant is own electricity, everything in the potable water plant is own electricity, and all pumping stations are own electricity. No, there's a lot of potential in that. Okay, now let's, what I prepared a little bit for this course is I want to do you how much common sense is in engineering. The most important thing is to train yourself in basics, and if you know the basics and use your common sense, you can solve most engineering problems. Engineering is not really difficult, but engineering is complex. So one of the most important things you're going to learn is to structure a problem and chop it up into units you can eat, no? As you can digest, and with your fundamental knowledge. And I want to show you this, how this is working, how you, with just very, or a certain amount, but not very much, of basic knowledge, which you can almost deduce also a little bit, most of it you can deduce by common sense. Well, a few things you just have to learn. This is why what your university education is for. And if you then have understood, you have to go structured to a problem, you can solve most problems. And chemical engineering is then to add all those pieces again and make a plant out of it. This is going to go a little bit beyond the scope which we can treat in 3 days, but I hope I can direct you a little bit. Okay, chemical and process engineering is the engineering and transforming complex materials with target-oriented methods and processes, which we call the unit processes, and products or environmental sustainable outputs. Chemical or process engineering is thus an important part of planning, construction, operating, optimizing plants, producing almost any kind of products, from recycling waste to products, and for treating waste for an environmental sustainable discharge or disposal. Waste incineration plants, putting paint on a car, all this kind of problems where you have to deal with chemicals is in the scope of chemical engineering. Most important methods applied in chemical engineering are mass, component, and energy balances. This is the tool which you have to learn. Mass doesn't fall from the sky and can't disappear. No, it's always because we have mass conservation, because we're not, unless we talk about nuclear processes, and okay, nuclear processes is a special discipline we're not treating here. Next to natural science background, mathematics, physics, chemistry, microbiology, and plant planning, structural, fluid, and thermodynamics, as well as physical chemistry, heat and mass transfer, CAD and CAM, construction, and automation control techniques are required. This automation, we don't need to make our own programs, but we need to understand how programming is working in order to give the information to a programmer how he can automate our equipment. Next, there's a planning process, there's a construction process, and there's automatization. In planning, that's what you have to do as a chemical engineer in most plants. You have to make your process scheme, you have to make your extended process scheme. In the process scheme, you have just the basic unit operations, which you need to get the process done, to come from your raw materials to the desired product. And then the extended process scheme is not more than just adding now the mass component and energy flows to that. And of course, the parameters and efficiencies of your unit processes. Then you find out if you get your product, then you know what your throughput is. And then the next step from there is to go to a PID. Who knows what who doesn't know what a PID is? PID is a process and instrumentation diagram.
Oh, yeah, okay, that makes sense.
No? That is getting from the, I always say software, from the unit processes, it's kind of like software, you go to the hardware. Now you say, because PID is what valves do I know, what reactors do I know, and then from there on, when you have your PID, I need a tank. Then you go to construction. You say how big it is, what kind of connections do I have, what technical equipment do I have. This is what you have to put in the PID, and then hopefully you find a mechanical engineer who is going to construct that, and that makes also life easier with structural mechanics, which we are normally not that good in. No? We have heard of it, but we are always glad if someone helps us. No, the better, like civil engineers and mechanic engineers are usually better in that. No? So let them do that. No? And the same thing is we got to describe, we got to be able to tell them what we want. No? And we need to know what's important. We need that for example, the weight loads on a surface or the weight loads in a tank. We need to know that we have to give that information to the structural engineer. No? Because he needs to know weight loads, wind loads, whatever he has to consider. That we have to so we can discuss them, so we know he's doing his job, and we have to know. We have to be able to understand if the structural engineer has processed all this information. So we need to have a basic understanding of that. Okay, this is okay. Now we shall on to the world of process and plant engineering. In Germany, we have almost a law which is called HOAI, which is the German word for this Honorarordnung für Architekten und Ingenieure. Also Germans love the word Ordnung. That's regulation. Honorar is something interesting. That's money. And so it's regulation for charging engineering and architectural services. And this is because the public public companies have also to give contracts to engineers and architects, and that's how they can pay the architects and engineers. This is because at that time when you give this contract, you don't even know what you construct. You know you want to construct a school, but you don't know how much it costs, and you don't know much what it looks like. And for that is this regulation. If it costs that much, normally you get anywhere between 10 and 15% of the costs that's later the building and the machinery and all the equipment is going to cost. That's what you invest for planning. And this regulation has another nice thing. It gives us a nice structure of how a consultant process or planning process is structured. It's structured in 9 phases. And that's what we're going to follow here. We're not going to follow through all the 9 phases. The 9 phases are basic engineering, conceptual engineering, then it comes to draft engineering, detail engineering, and then it's tender documents, then it's assistance in awarding the contract, and then it's site supervising. No, it's evaluation of the 6 is tendering, 7 is evaluation of the tenders, 8 is site supervision, and 9 is documentation and after-sales service. That means all the whenever defects and missing works and failures, how you treat all that kind of stuff, no? And we're just going to the draft engineering. That's basic conceptual engineering. That's what we treat, no? The basic evaluation. The first step of a project and planning is specifying the assignment in detail with respect to. Let me see, because I'm not very considerate about the time. When did we start? 1:30. About 1:30 we started. Do you want to have a pause of maybe 10 minutes or 15 minutes? Or I don't know, how do you do that? Because 1/2 hour was through. I was planning to do one and a half hour more today, and then having 4 1.5 hour sections tomorrow and on Friday.
Yeah, we can do that. That works.
Okay. You?
Yeah, that's fine. Yeah.
10 minutes break? Okay. Good. Fine. Fine for you, fine for me.
I should probably actually do it. Total solids and suspended solids. What's VSS?
Volatile suspended solids. You're known with total suspended solids. What else?
Suspended solids and then VSS.
Volatile.
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 Volatile. Okay.
Oh, sorry.
Yeah. Okay. That makes sense.
Yeah.
That makes total sense. Okay.
Volatil, das sind die organischen. Ja, doch, weil wenn du die heiß machst, sind sie weg. Volatile, ne? Das heißt, die Glühverlust. Ne? Was? Das Vorlesen. Ja, aber das. Sonst verlierst. Also erstens, was soll ich machen? Ich lese immer einen Absatz vor und dann erzähle ich was dazu. Weil ich kann nicht voraussetzen, dass Sie es gelesen haben. Wenn ich ihn nicht. Verstehst du? Ja. Ja.
byrjaði á því að gera staðla sem voru frá 1 til 10.
Já.
Þeir fara ekki nóg.
Nei.
Það er víst að gera 1 til 1000.
Já.
Það kom svona út. Ég sá að það var, þú veist, cirka hætta hér.
Ok.
Ég fór með það til Sjós.
Já.
Sýnda þetta. Hann fikk það í sig. Svo sagði hann,
Var hann ekki að meina að þú þyrftir að finna þínar lausnir, ekki staðarlausnir?
þetta. Þannig hann sagði, þú veist, ok, nú heldur áfram og þú notar þessa hérna,
Já.
sem þetta, finnur þessa 1 til 10, þennan finnur þú veist 1 til 2, hvert svona.
En þá ertu bara að fá þennan og þennan. Nei, ég skil ekki hvað.
Ég hef ekki náð að spyrja út í það, en ég ætla að segja hvort þú veist það.
Nei.
Af því ég sýndi þetta, hann var eitthvað, já, þú veist, þetta hættir að vera liðlega þarna, ég bara eitthvað,
Já, en þú veist, þarft eitthvað að hafa þetta, ég meina, ef það hættir að vera lífrið þarna, þá hættir þetta að vera lífrið þarna, þú ert með staðarorku.
já,
Og þá bara veistu, ef þú ert með sýni sem er meira í heldur en 150, þá bara þarf að finna það. Það er svona í öllum prófum, sko.
já,
Svo til þess að tekka þig af, ef þú veist ekkert hvað þú ert með í sýni, þá myndi ég bara renna óþynnt og renna það síðan þynnt 1.2, 1.5, 1.10, 1.100. Og þá er þetta botninn, þú veist, herða.
ég skildi það þannig að, þú veist, ég er með control sem er bara synthetic arsenicsýni sem ég veit hversu mikið.
Já.
Síðan er ég með það sama nema með kolum í
Ok.
og svo aftur það sama nema öðrum kolum í.
Ok.
Ég framkvæmdi allar þessar mælingar. Þannig ég byrjaði á control sem er með engum kolum og bara arsenicsýni. Gerði þetta hér. Allar þessar styrkleika af því,
Af
fengi
því?
hérna,
Að þú veist styrkin af því upphafi.
Já.
Já, ok. Og fjarstu þetta úr því?
Þetta eru staðlanir.
Ok.
Það sem ég fekk út úr því var þetta. Þannig ég, þú veist, mældi fyrst eftir engan tíma, eftir hálfa klukktíma, blablabla. Þetta er bara með engum kolum í. Þetta er bara, þú veist, bara arsenicsýni með engu.
Já, átti hitt að lækka þess með tímanum.
Það er það sem ég er að tjekka. Ég er að tjekka hvort það skiptir máli.
Já. En sko,
En, þú veist,
já,
hann sagði mér að gera þessa hérna concentrations út frá
af stöðlunum. Já, út frá þessu ársina standard.
standardin. Þannig ég bjóð til standard sem er 1000.
Já.
Bjóð til þessa hérna
Já.
út frá honum. Þetta eru bara þeir með engu í.
Ok.
Þetta er bara, þú veist, stock solution sem ég bara
Mhm.
setti í mini solutions og, þú veist, mældi
Og
það.
mælir síðan bara eftir einhvern tíma.
Já,
Það er þess að samt þú breytir það.
já.
Ok.
Svo ger ég nákvæmlega það sama nema bara með kolum í.
Ok.
Og þá líka með þess að sjá hvort þetta breytist
Já.
þegar þú veist, kolum sé að ná að taka meira eftir ekki langan tíma.
En sko, ég skil ekki þetta 200 sem er bara 100
Nei,
og 510 sem er bara 50.
gæti ég hafa verið að miskilja eitthvað þetta, sko. Ég held ekki en hann sagði mér að búa til þessa styrkleika. Hann sagði mér að nota, þú veist, bara sýnið og svo 1 kól og annað kól.
Ég verið kannski verið að tala um og ætti bara að búa til þess að það er lausnir að nota fyrir þess að búa til. Þetta er 1000, ekki nota hana til að nota.
Okay, back in business. So, well, after giving you a little bit of introduction, we'll now start with the hardcore stuff. Well, in the first step of project and plan planning is specifying the assignment. This is mostly underestimated and has to be done in detail with respect to all input and output mass and energy flows. That's what the basis also of a contract with your client is. For all input and output streams, mass and energy flow, all relevant components and their concentrations have to be specified, and the mass and energy flow has to be quantified. Mostly, if you want to produce something, they mostly have a market analysis, and they say we want to produce 100 or 2,000 loaves of bread in 24 hours or whatsoever. No? And they know what the bread is, and they know what the ingredients are. Somewhat more problematic is when we talk about wastewater. How much is it? No idea. What is in it? Less idea. No? Less than no idea. So this is, and even if you know it, we had this when we were talking about the hair cosmetics. No, we're talking about 200 different chemicals in there. Great. No, what does it tell me? Nothing. No? So there has to be a different approach to that. It is, however, therefore very important to limit the specification to only relevant components. And this is where you have to look, what do I know to design the process? This is where the engineer normally earns most of his money if he's doing a good job. This is often when you talk about students, they always say, well, we have to know everything, we have to analyze it. So why? Often you just don't have to know many things, because what's important is you just have to know what is influencing your planning. And sometimes it doesn't really matter if the viscosity is, you don't really, let's talk about viscosity, of oils and water and ketchup and I don't know what. You can now say, I need to know what viscosity it is in millipascal or whatever Pascal seconds or what we talk about. And what does it tell you? Often it doesn't even tell you. What you want to know is, can my pump that stuff? Yes or no? Right? Because if you're going to select a pump, and if you're taking now a peristaltic pump, that can pump almost anything which you don't have to shuffle. No? So you don't really need to know for that. So you have to ask you, how exact do I need to know it? Because you can make millions of measurements and you have to pay for every one. And if you have varying inputs, like I told you on this hair cosmetic company, they will not have every day the same production. They will have one day this is more stronger, the other day that. So you have different. And you need to know what is the range, what's min maximum, and can I live with it, yes or no? This is a decision you have to make as an engineer, and not to exactly know data. No? This is what means to relevant components are relevant margins of parameters. It is obviously impossible to specify all components of solid waste or wastewater, and it's unnecessary. Mostly, only a few components make up a relevant fraction of the mass flow, and many components are of no relevance for the process. Often, I will show you also, we come to an example which is related to biochemistry, which you will easily understand. Often, especially and widely practiced in environmental process development design, are some parameters used. I don't know how much familiar with that. Some parameters characterize the quality of inert effluents. Some parameters are TS, also total solids, SS, suspended solids. Those you can measure by filtration. VSS is volatile suspended salts. That's when you take the as a total solids. What's the difference? Total solids, is that with evaporation or?
Total solids, that's when you throw the material in an oven 105, 4 hours.
Okay, that's and dry matter, is that the same thing then? No? Basically, okay. Because we in Germany have, this is why I ask, because I'm not that in detail familiar, but this makes a great difference. If you talk about TS or SS, because TS, when you dry it, you have also the soluble salts in it, and SS is only when you filtrate it. And twice I had a problem. Once it was in the University of Darmstadt, and I suppose that the Sanitary Institute knows the difference between TS and SS, but they didn't. No? because and they let me believe, and it was in landfill leachate treatment, that by concentrating the biomass, I had a biomass of 12 grams, but actually I had only one of 6 because I had 6 grams of salts in there. So I was not meeting the criteria, and they let me believe that for 3 months. I could throw all the results for 3 months in the bin. The other one was they made me obnoxious in this dairy company because we had because they came up one day and said, we have a slight change in loads. No, I said, what is the slight change in loads? Well, phosphate is 6 times and COD is 3 times. I said, okay, that's a slight change, and then I have a slight change in money. No, also 6 times. No? They didn't really want to hear that. No? And in that we had a pre-treatment, and then they measured the sludge in TS, but half of it was lactose, and the other half was precipitated calcium phosphate. And I wanted to know how much sludge it was, and I was on the verge to order a centrifuge of double the capacity for sludge extraction. Before I found out they were measuring TS and on SS like they were supposed to do. And we really got almost in a fight because it was the research in R&D center of Ala Industries. And I thought, okay, but they have an R&D center, they should know the difference, no? They knew what it was about, no? Okay, we calmed down after a while, and everything went well. COD, BOD, COD is very important. Wastewater treatment is chemical oxygen demand. BOD is biological oxygen demand.
If you could, we've got kind of a diverse group of students.
Yeah.
Can you just explain BOD and COD, why it's important?
Yeah. For that reason I ask. COD is chemical oxygen demand. That is, in practice you use dichromate and sulfuric acid, and that oxidizes almost everything. And then you use that in excess and you titrate it back, and thereby you can use what amount of dichromate has been reduced by your by your sample. And then you can calculate how much oxygen was consumed. In BOD, the BOD normally has also a number behind it, and that indicates how long the BOD is applied. In BOD, as a chemical oxygen demand is something you measure, and that is the amount of oxygen is required to oxidize your sample. And the dichromate method covers pretty well 95 to 100%. No? In BOD, it's totally different because that is, you look at the oxygen consumption in the receiving water. It's a totally different look upon it because you use your effluent from your treatment plant, and that in industrial waste was kind of difficult because in a domestic wastewater treatment plant you have an integer microbiology in your effluent. You have sufficient bugs in there that will do your respiration. If you're an industrial, if you have cooked the water before, or pasteurized or sterilized it before, you're not going to have any biology in there, and you cannot measure your BOD. It's going to be 0, no? Because it's inhibited by the bugs, by not sufficient microbiology in your inoculum. You have to inoculate it. If you use an effluent of a domestic wastewater treatment plant, you have a wide range of microorganisms that are going to respirate most of the biologically degradable compounds. As in a wastewater treatment plant, we have, at the end of the day, we have a COD elimination of almost 95%. You will find that the BOD elimination is normally only half of that. Why? That's because the bugs in there, they just respirate half of it, and the energy they get from the respiration of these, they use to build up more biomass, because that's what they want. That's what they do their job for. So that's why, and it's about a 50-50 ratio, roughly. No, it depends a little bit on substrate and whatsoever. And so by this BOD method, that's the traditional one, and it had first in focus that you look at the receiving water, how much oxygen will be consumed in the receiving water. And then in former times, before 1960, at least in Germany, BOD was the parameter to look at, and people were calculating how much oxygen is getting into the receiving water due to its surface area, due to its flow as a fluid dynamics, no? That depends a lot, and for the oxygen transfer from the atmosphere into the water and all this kind of stuff. And then they said, okay, the river, the lake, whatsoever, this receiving water body is receiving 3 tons of oxygen per day. And so I can easily unload 2 tons of BOD per day into the receiving water, because then 1 ton of oxygen is more getting into the receiving water than is being consumed by the bacteria. So I'm going to have a sustainable DO, as a dissolved oxygen level, in the receiving water, which is guaranteeing the survival of my fish. Well, next to just the balance over the day, it's important that has something to do with the algae growth, that when you have a sufficient algae growth, then during the day when the sun shines and the algae grow, you have a nice DO of more than saturation. And when the sun goes to sleep, then the bacteria eat up the algae, and the DO is going to drop to 0. And your fishes, unfortunately, are not going to survive the night, and the next morning they are dead, and once dead, you're always dead. So the average DO is not giving you very good information. No, this is an important part you got to look at when you take about, because this is, we as water sanitary engineers, we like to have our waters, our receiving waters are the focus, to keep those in a good shape. And the most important parameter is the DO. Right? For salmon and fishes out of that group, trouts, salmon and trouts basically, they want the 6 milligrams DO per milligrams per liter. Right? And they want this, and 8 is the saturation, so you need almost saturation for that. So you need to have fresh water. But I was once in Nicaragua when I was a young PhD student in '86, and they got this village of Esteli got a grant from the European Union of 250 euro, and they were supposed to, at that time it was still marks or whatever, or dollars, and they were supposed to invest that in environmental things. So there was social scientists there getting this money and supposed to invest that in an environmental project. So he did the smartest thing. He went to the public administration. They sent him to the construction department. They sent him to the wastewater department. And those guys said, build me a sewer here and build me a sewer there, because this is where we have most epidemiologic cases and where we have the most children die. And we would try to reduce the death rate of children, and wastewater is the contaminant that's mostly responsible for our bad health situation in these regions. So he was on the verge of doing that. Then came a delegation of the Green Party, and they said, you can't do that, because you're not going to build any sewer with our money if you do not have a wastewater treatment plant. Because this water is going to go in the river, and you're just going to spread the disaster. We refuse to give the money free. Then I came with a few agriculture engineers, and they understood this right away, and they said, no, you have to build at least a pond treatment. And I said, no, you have to build the sewer. But first I said I'd like to see the receiving water body. The receiving water body was a river flowing at least with 2 meters per second. It was about 20, 30 meters wide, and it was shallow, so between 0.5 meter and 1 meter depth over this 30 meters. So you can easily calculate, not 30 meters by 1 meter or 20 meters. You have 20 square meters by 2 meters per second, so you have about 40 cubic meters per second flow in this river. This river flowing with 2 meters per second on a gravel ground. The gravels, none of them slimy, no? I asked, where's the next village? It's about 35 miles down the river. I said, okay, dump all the water in there that you can. because this shallow river flowing so fast had such an oxygen uptake rate that that the whole village didn't need a sewage treatment plant, to be honest. They could spend their money on other things more sensible. Because I think after 5 kilometers, you wouldn't be able to detect any BOD or COD in the water anymore. Because it was the purification plant. The river was so active in purifying wastewater, and it was natural, it was there. Because it had such a slope, no? That's why it was so quickly flowing. So as you know, in Germany in the 1960s, they decided, or the parliament of the West Germany then decided that our rivers are not our wastewater treatment plants. It was a law. So they said we want to have what we saw water quality class 2 in all our rivers. So whatever you do for wastewater, you have to clean it that far that due to discharging this wastewater in the river always is going to have water, at least water quality class 2. And that requires a cleaning. No? This is a political decision. But when you go to a country in development, maybe you have to look at different criteria. No? I told all of the social workers and also my farmers, I always say, those agriculture engineers, because at that time it was also, it was a lot of heart but not enough brains, no? To make decisions. It's not too smart. Because I said, you guys want to be responsible of children dying? To save maybe a bird who catches within the first 5 kilometers a piece of shit? I'm not. I have a different opinion or moral decision. I want the children to live, and because I don't see any damage to the environment. There is natural cleaning capacity. If you are in a society that can afford that, you shouldn't use it. Because when I went, I think that was in 1900, shortly before 2000, I was in Kaohsiung in Taiwan, which is also a developed country. There was a river in Kaohsiung called Love River. You could walk blindly on the side of the Love River, because by the smell from this cloaca, you could detect if you were 5 meters or 10 meters apart. No? It smelled so badly there. No? It was like in a toilet not being flushed for 3 months. No? So it was detectable. No? Now then we were like some years later there. They have now 2 big treatment plants. As it has developed within 20 years, the problem was a sewer, not the treatment plant. They were built faster, but they had not enough sewer. But in Taipei, for example, it's also an island like Iceland. It's only slightly bigger and has 20 million inhabitants, and only 50% is channelized now, as it is connected to a sewer, wastewater treatment plant. And this is, for example, Taiwan and also in the coastal areas of China, this is definitely a problem because they have a wastewater inflow in the treatment plant of 800 to 1,000 liter per person a day. In Germany, we have 100. How come? In Taiwan, the water consumption is pretty high because it's a tropical country. It's about 250 to 300 liters per person a day. In Germany, we're 126. But how come? How do you make out of 300 liters per person a day? How do you make 800 to 1,000 liters of wastewater? Any explanation? Well, you haven't been in Taiwan. Taiwan has the super fast train, and I have used it a few times. Going through the super fast train is not it. But what do you see? You see a rice field full of water. You see 2 ponds of carbs or whatever full of water. Then you might see 1 field which is not full of water. If you see all the surface with water, and if you see sewer systems which are only recently installed, which are not complete, there's malconnections to seawater and whatsoever. So you have all kinds of water going into the sewer system and also a little bit of wastewater from the households and industry. But most of the water comes from anywhere. But it's not stormwater and it's not wastewater. It's seawater, it's water from the rice fields, from agricultural wet areas or from fish ponds. There's all over water and when you travel through the populated area of Taiwan. No? And the same applies for China, for the coastal areas of China. No? So they have to do something as sewer systems. But that was even in Taipei, and one of the big. I was 3 or 4 times in Taiwan because a nice colleague invited me there for conferences. And in Tainan University, there was most of the times. And that operator, he learned. And he went after that, and he got it disclosed. And then at my third visit or something, pre-last visit, we were in Taipei in the big plants, and they really felt offended when I told them that they had so much mal connections. No? And they believed it was all normal. And it was 2 hours of very intense discussion before, and then the great help was that because they didn't speak that well English, the next problem, that this operator from Tainan, he said, no, Professor Pfeiffer is right. Think about it. Just look at your data. Look at your data. And he had made data from 2 years, and he presented his data, and he said, that's true. The COD is just COD inflow concentrations of 100 to 120 milligrams per liter. In my treatment plant in Wismar, we have 1,200. Yeah, it's 10 times diluted, no? The wastewater. So it's very hard to treat. You can't pay the treatment plant for that, and they have built treatment plants for this amount of water. So there are 3 treatment plants, and they were planning 5 more. I said, forget it. Put your money in your sewer systems. The 3 treatment plants can treat all the wastewater from Taipei. You just got to connect it right. And then they were disappointed their digesters didn't give them any gas. I said, well, if you just give me pure water in your digesters, what do you expect? No? Okay, this is how important, it's to know and to quantify and to really look and check and recheck and verify if your input data are right, are correct. Because you have to also cross-check your input data. We have a saying in Germany, wer misst, misst, misst. Wer mehr misst, misst viel Mist. That means the guy who is measuring data is measuring garbage. And if he's measuring more garbage. No? Because analytics is not very reliable. But by balances and especially if you go into industry, because it's so highly variant. We have millions of measurements on domestic wastewater, so we know that every human being, no matter if he's in Alaska or in South Africa, in China or United States, is shitting together 120 grams of COD per day. That's and 60 grams of BOD, 10 grams of nitrogen. It comes also from washing and everything. 1.8 grams of phosphor. Well, this can be up to 3, depends on what detergent you use for washing your clothes. No? But this is about, and then how much water we consume is very different. Germany with 126 is pretty low. Jordania with 20 liters per person is lower because there's not all over potable water installation. And South Africa is also with 35 or 60 because there's a lot of these slums where there's no water connection. A lot of people are not connected to that. And then they, of course, carry water only 20 what they need. No? And United States was at 350, Switzerland and China and Taiwan on the top ranking. In the United States, it's mostly the southwestern area because they use a lot for watering their gardens. No? So it's a little bit different. But there on the water, on the quantity, you have to look. That varies. But the how much it is from human beings, we know exactly. In industry, it's quite different. In industry, you got to make all kinds of material balances. How much water goes in? No? And comes any water out of the product? Well, yes. If you produce cheese, no, and lactose, and then all the water that's in the milk, you try to get rid of. That's of course in your wastewater. No? If you produce beer, comes out less water than you come in because they make out of the water they make beer. Same thing with the bread company. No, they sell bread is nothing like the boss of this factory told me is water you can cut. No, we sell water cuttable. That's what he always said. And ice cream people say, well, we sell air. We sell air packed in cream. That's what we sell. No? So it depends. No? And so balances, then you got to compare, what's the word for it? Benchmarking. You can look at different companies. Because like my company now was 2.6 cubic meter wastewater per cubic meter of raw milk processed. That's terrible. When the first company I started was 1.7. Now we're down to 0.9. So we're in the top ranking in Germany, and they're top ranking in DMK, which is the biggest group, and also with wastewater cost. That also lowers cost. So you got to look in the industry very detailed in the production process. Has it to be necessary? What are doing the lot? You have to go in there and look. And you have to see where do you find the wastewater. The production engineers don't know. Even the nice guys in DMK where I worked, first because when I got the first contract, when I became professor, I just got this contract. It was pretty nice, and I could build for 2 million a wastewater treatment plant. And when I was done, they decided not to build a new factory as was the plan, but they decided to double the capacity where I had just built the plant. So I got a new contract to expand the plant for another 1 million. Perfect. Was 6 years of work, great. No? And when we planned for that one, with the production engineers and nice guys, we tried to say, well, by this expansion of the factory, how much more wastewater do we have to expect? At the end of the day, when we calculated from the production side, it was less freight as load, COD load, than we already had. So I said, okay, forget it. No? You guys don't know what's happening in your company. No? I'm just going to go linear and hope that will happen. No? And it more or less came out that way. And another company, we subestimated bottle cleaning. No? In this brewery where we were, this production engineer, he told his manager after talking to me, I don't know what this guy is for. Is going to help us? No, he has very conventional things. No, I don't think he's going to help us. Then the CEO said, no, we're going to do what this guy says. I want to see your production. He didn't want to show it to me, so he showed it to his boss. And what ended up, they found 1/3 of the COD load is in 1 cubic meter, and all the rest is in I think 60 cubic meters per day. It's a very small. It's it's like a craft brewery with a hotel and a restaurant with it, and so in this 1 cubic meter, they bought a tank for 20 cubic meters. They discharge it there. They collect it in an ICP in a craft brewery. They just drive it over, dump it in this 20 cubic meter tank. We put it outside of the village in a field, and there comes a truck, gets that, and brings it back to a biogas plant. The whole thing is going to cost us this 35 cubic meter euro per cubic meter, but they save over 100,000 euro in expansion of their existing capacities. They just can now we can expand it for 100,000. Else we would have needed 200,000 investment. The cost of this 35 euro per day, that's times 200, is about 10,000 a year. So for 10 years you save it, and in 3 years they get connected. So of course it's a smarter decision. No? Of course you've got to look at that. No? So this is a few examples, and I gave you the other with Brad company before. This basic evaluation pays only 3 to 4% of the of your consulting fee, but it's utterly important. If you make mistakes there, the whole project might go wrong. Okay, others are alkalinity, which is the capacity to buffer acids, conductivity, bioburden, that's something for Sean to explain to you. It's counting bacteria, that's nothing for me. And there's other ones. No? Okay, as analysis are costly and only cover the analyzed samples, one of the most important tasks of a planning engineer is to make a correct load assumption with respect to the planning horizon. And there's now 3 problems in there. I got to make a load assumption, and I shall do it without measurements, and I shall do it for the future. Because if I going to construct the thing, it shall be good for next 25 years. 25 years is what is the of any plant life. No, sewer life is 50 to 100 years. It's even more difficult. What happens when you sometimes we installed a DAF, dissolved air flotation. At that time, it was a packing house, and when the plant was installed, the packing house was bankrupt, and the convenience food company had bought the installation, was making totally different products. And that was before I entered the company when they made the contract, and they had nothing limited. So those guys from the convenience company went, hey, we have a contract. You have 90% of cleaning efficiency. And my guy said, hey, this is totally different products you're saying. Yeah, bad luck. If you don't do your contracts right, if you don't do your basic evaluation right, if you write the wrong things in the contract, bad luck. Took me a lot of discussion to find a way out without paying too much money. So this is also, there's different dimensions. First of all, normally money is the third or fourth priority, because the money will be okay if you do a good and right job. No? So the first thing is to do a good and right job in engineering, and that means you have to make a basic evaluation. As an engineer, you're not a wizard, you're just an engineer. So the only things you can do, you can work with the data you got. And with those data, you've got to work correctly. Don't do wizardly things. That mostly goes wrong. So for sewer systems, I just said that planning horizon is 50 to 100 years. For wastewater treatment plants and water purification plants, waste incineration plants, it's normally 20 to 30 years. For plants in industry, it's normally 10 to 20 years, although they are more often it's deinstalled after a shorter period of time. Sometimes it lasts longer. So an average is maybe 10 to 20 years. Often no measurement of the input loads are possible because you stand in front of a green field and you can't measure anything in a green field because the plant is only being built, and at the same time you've got to build the wastewater treatment plant for this plant. Simply because they are not available. The load assumptions are often the insecure assumption in plant planning, especially in planning of environmental plants like wastewater treatment plants or waste incineration plants. Reference data from similar plants, even if anonymized, are often a great help in assuming the load to the plant. Predicting the development of the load of the plant into the future for the period of planning horizon does not make load assumption for planning engineers any easier. No? So it's just a difficult, and of course you have to discuss a lot with the people to find out what's possible. Since if you're not in bakery business, you got to talk to the people. What do they expect? What's safe? What's not safe? For a sound assumption, thus, a thorough preliminary feasibility study of the project is often required. All stakeholders should be involved in the study and should agree to the result that shall be the basis of the process development and design if draft process study proved the feasibility of the plant. Especially in the planning of environmental plants, it's most important to study thoroughly if no load to the environment plant can be avoided by optimization in the product processes. Because nobody can pay a wastewater treatment plant for treating raw material, because then you pay for the raw material 3 times. Pay the raw material, pay the treatment, you pay the sludge treatment and disposal. No company is going to survive that. Due to my experience in planning of wastewater treatment for industrial, I mostly reduced the wastewater treatment by 30 to 50% due to optimization in the production. That's normally what you find. Also, I told you the bread and brewery, the examples I already commented. There's also an interesting approach, but how go about sizing, what to build. When the people from Bayer bought a nearby biotech company, which I was involved a little bit in wastewater problems, I was also in there when they said they're buying a new territory because they want to expand the production and the R&D department. So they bought 2 lots next to the existing company, and we were doing all the planning of what we needed for expanding we made a room book and what is in every room and how much rooms do we need, what size do those rooms have, what is the infrastructure and so on. So then the buyer people came, looked at that and said, that's nice. And they said, we're not interested in that right now. That comes later. What is allowed to construct in this lot? Yeah, we are going to build what's allowed. 6 meter high, how close to the border can we get? And that's a building we're going to construct. And then we're going to talk what's inside. And there we also have certain measurements because he said we have so much experience selling houses we have been in use. We have almost not been possible. So our policy now is to always construct, if we construct anything new, to construct what's allowed, the maximum. Because anybody who's going to buy the lot can't construct anything more. So he's going to buy our building. That's the only way we can resell our building. Because whatever we construct, what we need, the next user is not going to be happy with it. So we'll not get good money for it unless we build it as big as possible. Because then the next user can say, you can't construct more. Buy it, it's the best you can have. It's kind of an interesting philosophy, I thought. No? Because normally, if you construct anything, the size is not really giving much on the cost. Later expansions are much, much more expensive. So this philosophy makes sense. Today, however, upgrading of or optimization of a plant is a more frequent request than planning on a greenfield and an entirely new plant. In upgrading optimization, relevant data are available or can be made available. Data shall be analyzed in time variation curves for seasonal, monthly, weekly, daily, or hourly variations. Are you familiar with time variation curves? Okay. That means you just get measurements and you do that over 3 years normally. You try to get not every day how much cubic meter was, and then you make this in a curve. Yeah, something like that. Huh? And then you see if there's any seasonal influences and so on, and you look at that. The measurement you must make what's relevant for your planning. Like, do you need what is the residence time in my plant? And then I need to know, based on the residence time, I need what is the maximum capacity of this plant. This is what I need to find out, because a plant has always to work, right? Like in a domestic wastewater treatment, it's easy to understand. That you can tell the people, okay, on Christmas, when you get a lot of visitors, half of the visitors have to get a stopper because our plant has not that capacity. Something. You understand? No, this is why the peaks things are, and then you see this, and the other is a sum probability distribution curve. That is, you take all the data, very easy with Excel. You sort them from the lowest to the highest value. And then, when you have it measured every daily, the period is always the same. Thus, the probability is always the same. So zero is zero probability, and your highest value is 100% sum probability because that's the highest value. And in between, you just make a linear because all have the same probability. And then you make a graph of your numbers, which you measured over the x-axis, and a probability from 0 to 100% over the y. And then the 50% is now not your average, but it's your median value. No? That's simple statistics. You can read in any statistics handbook. And then you see, because mostly laws in environmental things give you a probability. Like you have to meet the standards, at least in Germany, you have to meet the standard with 80% of probability. That has something to do, for example, In wastewater treatment, again, domestic is a good example. You have to deal with stormwater. Yeah, you can't treat 100% of the stormwater, and it's not necessary. Because if the stormwater is diluting your wastewater by 1 to 100, and that's possible, that's easy possible, because dry weather flow is very low in comparison to stormwater flow, then you have already 99% of cleaning efficiency by dilution. That's not really cleaning efficiency, no? But then also the flow in your receiving water is much higher. So you get more oxygen into your receiving water. That's again where you use the self-purification capacity of your receiving water and water economy. And else you would have to build like subway tunnels for wastewater if you want to have the 100-year maximum water for your sewer system. And don't talk about the wastewater treatment plant. It's going to require more area than the entire town. And that obviously doesn't make any sense. No? Due to that considerations, you got to find a way to handle that and say, this is the probability I can accept, and whatever is, I always told you in industry, always talk about a hazard tank. And there you say, okay, those loads of those 2 or 10% of the days, I'm gonna reduce by my hazard tank. No? In order to handle this. This is very important when you evaluate your data. No? Okay, now enough for information, generally on quantifying your or specifying your amendment of what your job is, what you have to do, and how to qualify and quantify it by some parameters and by data evaluation and time variation curves and some distribution curves. Okay, the second part of basic evaluation is that you clarify the construction site situation. On the one hand, the construction site requirement might be defined as there are available space, heights of the containment, that depends on your reactors, openings for insertion of equipment, infrastructure requirements, if you need a street, if you need a train connection, if you need a quay for ships, it depends, no? Wastewater, water, gas, electricity, communication. No? You got to find out, is there lines for, so when the how do you call this guy here, who digs up the backhoe? Backhoe?
Yeah, I think that's what it's called, the
Caterpillar or whatever.
Scoopy thing.
The Scoopy thing, no? This thing, that digs up the earth, no? When he comes, you better know where the gas pipe is, no? Else you're gonna have a big hole and no bagger, no construction machine anymore. No? The hole is there, but no construction machine anymore. You are in jail, no? Because the operators not exist anymore either. As the gas pipes, you better know really, and the same is that you don't destroy existing pipes. No, we destroyed once a communication pipe. We forgot. No, glass fiber you can repair, so it's not. But that happens. No, as existing and what you need later. So you plan those connections. No. On the other hand, for sites, ownership, existing rights of other people, lines, pipelines. Quality of building area, very explicit. The bearing capacity, what kind of fundamentation you need for construction, groundwater table, foundation requirements. This is all. This can considerably generate costs, no? As well as protection zones, landscape, ecological, drinking water abstraction, berg, sanctuary, and everything else. Because you might plan it, it doesn't help if you don't get permission later to construct it. No? Okay, that's all to basic evaluation, if there's not any questions.
I just would like to state that I'm really surprised that going back and optimizing existing processes is such a large factor here. Because but by the time somebody actually comes to you to look at the wastewater side, you would think, wouldn't established personnel already process to take advantage of those savings? I
very simple. This guy who was in charge of the spread factory, he said to me, Professor, it's very easy. I have 40,000 euro to pay monthly for wastewater. That was before I came. After when I left, I had paid only 19,200 a month, every month. So we're talking about 240,000 euros a year. And he said, and you can't hire an engineer for that? He says, no, I can hire external people for that, but they will not permit me any more engineers. We have 6 engineers in this entire company with 200 employees and with 9,000 tons of bread a month. No? He said, I have 400,000 euro labor cost every month, and I have 4 million euro raw material cost. And now you can see what my engineers are doing. First, we have to see that the raw material gets through. Was the least loss that we can have. And we didn't see this 100,000, and the 4 million. We didn't see the 100,000 in the wastewater. Of course, it's a lot of money every year. And then we have to see that we get our labor force organized, and that we get our products out. And for the rest, we just don't have any capacity. He said it's very easy. To you, just send me an offer, and I'll sign it. I won't even look at it. No? You got at least 5 offers free that they are not going to work out, no, because you already earned your money, no. He said you can give me any offer, I sign it, and I get the money for it. That's not the problem. I won't get an engineer. That's company policy. That's the intelligence of BA people, I always say, no. No, BA people are saving money. Yeah, maybe not. No. And that's not one company, no? There was a guy from in this biotechnology company. I had a student doing an energy survey, no? So we found out that the steam generator, how much steam they used. No? I said, I want to evaluate where is the steam going in the process, how much steam do we need. So we had just 2 sterilizers. We know how many sterilization processes they did a day, so it was pretty easy to calculate. No? And then we find out how much gas, natural gas, are we consuming per day going to the steamer. And we found out that for the steam generation, that the steam that was used for processes, only 25% of the natural gas consumption was realistic. So what happened to the other 75? Oh, very easy. You just got to look at it. In a steam generator, you produce steam. With the steam, you go into the processes, and you have an internal consumption in order to preheat the water in order to get the oxygen out of the water in the preheater, no? To reduce the dissolved oxygen in order to reduce the corrosion. And then finally give a little bit sodium sulfite in order for getting it down to 0, because reducing. Okay, there is a valve, of course, which is controlling the temperature in this preheater. And those guys that sell those preheaters, they always, that sell those steam generators, they always adjust this to 95, as that it gives gas-free steam, injects steam in the preheater if the temperature is below 95, and stops if it's more than 98. Sometimes 96, 98. So this valve is constantly working. It's 12 bar steam on it. So it has a lifetime of maybe 3 to 6 months. This valve has a cost of about 500 euro. So what the operator do, he changes it twice or 3 times, then he gets tired of it, he puts a manual valve in it, and he adjusts it. And that's what happened there. And so the cost of the natural gas wasted was 2,500 euro a month. Then this guy, then it took him 3 months to get the valve, and it took him another 3 months to put the valve in. So I said to this boss from the company, the CEO, to the plant manager there, I told him, you know, why don't you just take it off his salary? I think then you will find the valve is going to be installed within a couple of days. Well, he said, I can't do that. No? And this same person who wasn't able to install this jam, he told me, I came once and said, you know, I'm going to put here a co-generator. It's natural gas, and I'm going to supply you with electricity. And he says, well, forget it. This has, because we in Bayer, we have a ROE, as a return on invest, of about 2 years. And if you don't meet the 2 years, the project is not going to be approved. Again, BA philosophy of Bayer. No? They buy Monsanto and they are bankrupt, close to bankrupt, but anybody else is supposed to get an ROE of 2 years. No? So I told this guy, I said, you know, this is very easy. I said, I'm going to put the co-generator, and I'm going to supply you with energy with contracting. And I want to see anybody who's going to refuse a cheaper contracting than buying it somewhere else. This is not even Bayer's doing. And I'm completely satisfied as I have an ROE of 5 years. Maybe because 5 years is 20% on my investment. And if any bank would tell me, I don't know any investment where I get 20% of interest. No? Then he looked very surprised at me. I said, yeah, I'm smarter than you. That's a difference. No? Well, okay, that's okay. Any other questions? Sorry. Okay, and then we have preliminary. The next step, if I have now my assignment done, I need to do some preliminary planning. That's what I also called concept planning, because that's where we make the process scheme and the extended process scheme and rough cost calculations in order to find out the most favorable solution. Okay, in the second step, implementation concept for the assignment have to be formed from process schemes by arranging unit processes or unit operations target orientated. This implies that I have to know unit operations. What are unit operations? Unit operations are heating, mixing, grinding, sedimentation, flotation, filtration, whatever. Any of those processes is a unit process operation, distillation, rectification, and so on. We accumulate a little bit back because those are thought in chemical engineering, because chemical engineering has 3 areas. It's mechanical engineering, and I'm going to present some unit processes of mechanical engineering. Then we have thermal process engineering or thermal separation processes. This we hardly have in wastewater treatment plants, so this area we will not touch. This is an important thing, what you find in any crude oil refinery, that you will find there all this distillation, rectification, crackers. There you find all those thermal processes. And then finally, you have the chemical process engineering, and that's where you have chemical reactions. We, in a subfield of the chemical process engineering is microbiological engineering. This is where you use microorganisms to catalyze the chemical reactions you want. And that's what we're going to treat as well. The mechanical process engineering we're going to touch because the wastewater treatment plant, and we're going to treat that for domestic wastewater that has a mechanical treatment part and a biological treatment part. And in the biological treatment part, it's not cats and mouses and rats and dogs that are doing the work, but it's microorganisms. That's why we do there microbiological process engineering. A process scheme is arrangement of unit processes in order to realize the desired material transformation from the raw materials or the input to the products or an environmental harmless output. This is the most creative part of the process engineering. alternative process implementation concepts shall be elaborated and compared. You know? And this is also, you should be, here you should not limit yourself too early to say this is a standard solution, because this is where new ideas come up, where new things are. There are some schools of inventing. There's a guy called Schuler. I forgot his first name. He was in a Soviet gulag in a Soviet Luxus gulag, because he was allowed to study 40,000 patents in his sentence time there. And he evaluated all those, what is the structure of these ideas. And he came up with a few rules, and 30 years later, a consulting company in Boston took up the Schuler ideas and made software for that. It has been taught in our school for a time. It was kind of interesting. I didn't find it lately. I didn't get the ends totally together. But what I found fascinating, that this Boston consulting company had 2,500 unit operations listed and described. That was from gluing, from all kinds of mechanical treatment of materials to produce a certain tool, or to produce a certain mechanic item. No, also, it was very wide arranged. But I think if I know if I get up to 200 or 250 unit operation, I think that's probably the most I can think of. And they listed at 2,500, and just by scanning through the list, there were plenty of them. I couldn't even imagine what it's about. No? And so this is also something where information technology can help us a little bit in the future of finding a process we never heard of or we never have an idea, which we do not consider at all. Some of them might not even help, because the ideas which Mr. Schuler presented in his book, which I partly read, were a little bit exotic and wouldn't really work. For example, electric filters for waste gases exist now, and he had some of that ideas. Maybe some of them come up. No? There's also in Japan, in the company Honda, the old Honda, initiated a museum for impossible ideas. They, for example, made a bike with square wheels. No? And these type of two square wheels, then you have kind of it was in the first moon rover realized, no? Because it could climb and everything else. No? So, and the old Honda said there's no ideas which are worthless. No? It just is a tool, it's a task to find the right application for the idea. No? Okay, we don't want to go too much in philosophy here. Killing criteria for a process alternative is that either the required product quality is not met, or that the process is not licensable. If you find that out, you can close that book. That's not an alternative. Any process has to meet the criteria, also the product quality and quantity criteria, and it has to be licensable. If it's not licensable, you better don't build it, because they are going to close it down. No? For all process alternatives that meet the required product quality and are licensable, the most feasible process alternative has to be identified on the basis of annual costs. There's almost no other criteria in process engineering. This kind of interests my son studies mechanical engineering. If you have a product construction or design, there's non-commercializable criteria, there's a non-monetary criteria on it. Ergonomics, for example. How are you gonna evaluate that? And that comes when you get to those what do they call those boxes where you have all the criteria and values for evaluating the criteria. This is double much or twice as important as the other criteria. Hier von Schneegast, die heißt die. Ja, und da hat er doch diese Kästen, wo der immer dann kommt unten raus, das ist so nice, das Product. This is when you speak in two languages. Normally, I hate this because it doesn't work, because the students always come up with that. No? They always want to make this a non-monetary criteria, and there's not many in process engineering. So process engineering, it's because nobody cares if a plant looks nice, no? Or if a plant is ergonomic. This is almost no criteria because no one works at it. If it's good control, of course you have to be able to maintain it, no question. No? But this is not really a criteria. This is just good construction. No? And so we don't have this criteria. But in mechanical engineering, yes, it makes a difference for the mechanical products. If a bicycle, if it looks nice, if you sit well on it, but it has nothing to do with the cost of the bicycle. No? Okay, so annual costs are the sum of, because a lot of students just don't know that. That's a little bit basic business administration you got to know. The annual costs are the sum of annual capital and annual operation costs. And this is nothing that's visible. This is very simple because capital costs are the sum of amortization, and you don't need to fall asleep when you heard that word, amortization. Or faint out, no, because it's nothing so complicated as BA people want to make you believe, because it's simply the sum of the interest of the investment cost and what you have to pay back the loan which you took. So operation costs are the sum of costs of labor, energy, consumables, maintenance, and disposal of wastewater, salt waste, and of insurance, etc. A few things, but these are the main list, no. And since insurance and all this is normally all related to investment costs, no, you can touch that out or give it a certain percentage. For example, maintenance, you normally say it depends a little bit on civil engineering, and mechanical and electrical engineer is a little bit different. Mechanical engineer is 4%, civil engineer is 2% of the investment, then you're on the safe side. No? So this is not really complicated, and for comparing processes, it's far less complicated. So don't let the BA people do that yourself. No? For process alternatives with overlapping feasibility, planning has to be elaborated further until one of the processes can be identified as the most feasible process. So killing criteria is function, is process safety, is process product quality, process stability, and process efficiency. This has to be met. No? Licensable is process safety again. This is maybe overlapping, but you can't risk that anybody's injured or worse. Licensable is also process emissions. You got to meet all the emission laws and standards, and environmental conflicts, of course. This is what has to do with these defined zones, archaeological bird zones. No? There's certain restrictions where you have to meet sound and whatever other emissions. No? Economic criteria are mostly annual costs. Capital costs are the sum of amortization, that's paying back the loan, and interest rates. No? Normally, amortization already includes the interest rates, because when you buy a house, no, it's very simple. You pay back your house in 20 years, and you pay always back in 5% or 10% or whatever, and then at the beginning, most is interest and little is amortization. At the end of the paying, there's only little interest because you pay back most of the loan, and there's much amortization. No? And this is a little bit a function, but that's pure mathematics. Look at it, and you're going to understand it. If you don't understand it, you should consider if you are right with engineering, because it's mathematics. You should be able to follow up. Okay, operation cost mostly is labor cost, which is mostly independent of the process. It's not that process related. Maintenance costs, that's very much process related. Consumable costs is mostly always also the same. It's process independent. Energy costs is a process dependent. So we end up with maintenance costs, energy costs, and disposal costs are mostly always the same, because you're not allowed to waste any of the raw material. Then process engineering, that's what I told you. Mechanical, thermal, and chemical process are distinguished. No? Special areas of process engineering are microbiological, biotechnology, or nuclear process engineering. mechanical, as a process engineering, separate mechanical engineering, thermal engineering, chemical engineering. The mechanical engineering has to do with, it's even in German a hard word, in English even, dispersivity. Yeah, dispersivity. Anybody knows what dispersivity is meaning? No. It's a complicated word for two things. It means mechanical engineering has only to do with the distribution of one phase and another. That's probably solids in a fluid. A fluid might be gas or water. This is mostly of it, no? So dispersivity has to do. You can look it up. Dispersivity. You can look it up in the dictionary, and it's going to tell you exactly. This has to do with one criteria is a concentration. I looked it up in Leo. No? So I think it's right. Leo is the translator of the Technical University of Munich, because I wouldn't know how to translate. Dis.
That's why I'm like, why is there a
Dispersivity. Okay. Okay, and then I have to change that. I do that at home. Yeah, there's it, right? Okay, so I just missed it in the. It was too late when I made the table, obviously. Okay, dispersivity is one criteria is a concentration of the dispersed phase in the continuous phase. No, continuous phase mostly is a fluid, and the dispersed phase is the salts or the bubbles in the fluid. No? And is how much is it? And the other thing is the size distribution, form, and anything that goes with it. No? The size distribution, for example, you can influence by salts if you mill them or anything. And the concentration, okay, you can influence by separation processes or by mixing processes. And this is what we talk about here. So we have the two things, separation of phases and particle size distribution as a to influence that. And then this is what the task of the mechanical engineering is, and this is what is a selection of unit processes: sedimentation, flotation, filtration, mixing, disintegration, agglomeration. Nicht for disintegration, there's, for example, milling, crushing. There's a bunch of different ones, and sedimentation, flotation, filtration, centrifugation, as a sedimentation in a gravity field or in a centrifugal field. You can still distinguish, but I think then there's not that many processes more, because if you talk about membrane processes, you are really talking about thermal process, not about a mechanical process, although mostly it's treated in mechanical engineering. So in thermal engineering, it's mass transfer from one phase to another phase. And that's transfer of components, for example, absorption out of the water onto the active carbon, things like that, from one phase to another, sorry. And these processes are distillation, rectification. This is where you work with the partial pressure. Absorption, adsorption, absorption in a liquid, adsorption on the surface of a solid. Desorption is the reverse process of ab and desorption. And extraction, which you as biotechnologists know very well. No? That's your everyday business.
Yes, a word I know.
Okay. Well, chemical engineering has to do with chemical reactions. We talk about modification of components through chemical reactions, and there's only 4 reactions we deal with, besides, of course, association and dissociation. That's something I wouldn't consider a reaction. And then this boils down to oxidation, reduction, disproportionation, I had to look that up, and symproportionation. A disproportionation is when you have anaerobic digestion is something on it. You start with sugar. On the sugar, the virtual load of the carbon is plus minus 0, because the virtual load of hydrogen is always plus 1, of oxygen is minus 2. If you have HC6, H12O6, you have 12 plus from the H plus and 12 minus from the 6O. So what's left over for the carbon is 0. No? And then when you go into disproportion those, it's that the reaction of the anaerobic digesters, you produce carbon dioxide, which has, of course, a +4 virtual load on the carbon, and you have oxidation number. Is that right? Oh, the oxidation number is +4, and on the methane CH4, it's -4. No, you get out of one sugar or glucose, you get 3 of each. No, you get 3 of each. Then you have your 6 carbons. The 6 carbons, the 6 oxygen are gone, and the 12 H plus are gone. No? Oxidation numbers are the key to equilibrate all reaction. Gleichung, what's this? No? Or to make the reaction formulas. No? Also oxygen to balance them, to balance the chemical reactions. This you always need to consider the oxidation numbers, else you can make very simply you get garbage. No? First is look at the oxidation numbers, get the lowest common divisor, and then look at the electron transfer, then look at the external loads, and then at the end of the day, balance the hydrogen and the oxygen, because you can do that with water. No? And for balancing the external loads, you can use H plus and OH minus, no? Because in water you have all those available.
So if you're using enzymes, you would put that under the chemical engineering part. So it's like chemical reactions, whether they're biological or not, they go into there.
Yeah. Whenever the component is chemically changed, then we talk about chemical engineering. Exactly. Yeah. No matter who is a catalyst. No? If it's a living catalyst or a dead catalyst or no catalyst, it's me. No. It's for me as a crude chemical engineer, bugs are only catalysts. With the
Fourth box for biological
no. In German, we have a saying: all good things are 3, and that's why I love to make things 3 by 3. I think because that's really true. 3 things you can memorize very well. So due to that, it makes reason. So mechanical dispersivity characteristics of single and multi-phase systems are modified by mixing or separating phases, or by modifying particle or drop size distribution by agglomeration or disintegration. Mechanical separation processes are sedimentation or flotation and filtration. In sedimentation or flotation, the driving force is a difference in density of the different phases. This sedimentation is mostly used in the gravity field, but sedimentation can be intensified by sedimentation in a centrifugal field, in centrifuge or cyclones, no? Hydrocyclones or air cyclones. In gas cyclones. In filtration, particle size and particle form are the separation criteria. Separation is always a separation criteria. You always got to think, if you use a process, what is the criteria? Can I use the criteria? This is an important part, because if the criteria doesn't match your task, you have to use a different criteria. And I'm going to show you how this how with this simple thinking you can select the right unit process for the chain of the different processes we are going to use in a mechanical separation process we are going to use in a wastewater treatment plant. This is what we do tomorrow. So particles that do not pass the pores of a filtration media due to their size are retained in filtration. All these mechanical separation processes are applied in wastewater treatment plant. Also mixing and stirring is applied in wastewater treatment plant. Processes of agglomeration disintegration are applied in wastewater treatment plant only in a very special form, and this means flocculation, and so that's almost that's a very specific task. We're not going to treat that here because that's too complicated for first course. And mostly there's no theoretical approach. Just call someone who sells you that stuff to show you how it's done. And if he can't do it, call the next guy. That's normally the procedure how to do it. In thermal separation processes in multi-component or multi-phase system, different mass transfer rates and the equilibria from one phase to another phase of different components separates components. In distillation, for example, alcohol evaporates at a higher rate and equilibrium concentration than water due to the high vapor pressure of alcohol in comparison to the vapor pressure of water at the same temperature. In condensate of the distillation, thus the alcohol concentration is higher than in the feed of the distillation sump, or in the distillation sump. There, the water concentration is higher than in the feed. Other thermal separation processes are rectification, absorption, adsorption, desorption, extraction, etc. In wastewater treatment, only the thermal processes of absorption, desorption, and absorption are applied. We are not going to treat those either because it's active carbon. And this is not really too much applied in wastewater. It's rather in groundwater sanitation processes and this kind of stuff. And chemical processes, chemical reaction takes place. Chemical reactions we shall consider in this course are dissociation, association. Here I included them. Oxidation, reduction, dispropionation, and synpropionation. I gave you an example for dispropionation. Synpropionation, for example, is the Anomax process. In the Anomax process, we combine ammonia and nitrite. Ammonia, we have the N with -3 and nitrite with +3, and they react to elementary nitrogen and water. No? And there it's kind of important that you look a little bit on, their hydrogen, that's easy, that matches. But if you have a look at the denitrification or at the nitrification, there you have that acid is generated and the nitrification recovered to 50% in the denitrification. That's where it comes, where you have to look at the oxidation numbers and external loads, else you're going to balance your chemical reaction not correctly. Chemical reactions occur in nature under ambient conditions and temperature. Many of the reactions are catalyzed by microorganisms. Others only proceed in geological eras. No? In technology, reactions are intensified. Reactions can be intensified either by forced reaction conditions, temperature and pressure, or catalysts. Reactions are thus intensified by increasing the microorganism density in a reactor or by supplying the reactor optimally with required EDOX, like in example oxygen for oxidation processes by respiration and optimal reactor conditions for the microorganisms, like in example mesophilic temperatures for the anaerobic digestion for converting organic waste or wastewater contaminants into biogas. This is just to organize a little bit the chemical process engineering. So we have, for the same process, we have different words in biology, microbiology, in wastewater treatment, and chemistry. In microbiology, we talk about photosynthesis. Most of you know what it is. In wastewater, that's the only application of photosynthesis is algae growth. In chemistry, that's reduction. No? Because the process reduction is always coupled with oxidation, obviously. But the reduction is the process we look at. That's reducing the carbon dioxide to sugars and comparable organic substances. Respiration is just a reverse reaction. In wastewater, we talk. We have the word aerobic degradation for that, and in chemistry, it's oxidation. The fermentation and in microbiology, we call in wastewater treatment anaerobic digestion, and in chemistry, it's a dispropionation. And the same is the anaerobic ammonia oxidation, an Anomax process. That's an anaerobic ammonia oxidation. It's the same here in wastewater treatment, but it's a synpropionation in chemically, and in a view from chemistry. Under forced conditions, high temperature and pressure reaction often render byproducts. This is a main difference, and this is why chemistry, first of all, to produce forced reaction conditions is costly sometimes. That's why you have to have a higher value for your product. And the bad thing, if you want to do it environmentally sound, is all those byproducts. Microbiology catalyzed reactions follow the microbiological pathways and are really very selective in respect to intermediate and final products. There's almost no byproducts. No? This is the strength of the biotechnology, biochemistry. Not all reactions, however, can be catalyzed by microorganisms. The reaction rates under forced conditions are mostly much higher than the reaction rates under microbiological catalyzed reactions. That's the reason why long the microbiological or biotechnology didn't play a role, because nobody was interested in the waste or in the effluents that was only dumped. No? And that was it until the 1970s, when environmental consciousness started. And then it was only money and price. And there, of course, since plants were pretty expensive and energy was cheap, it was always the forced reaction conditions that made the race in the feasibility. No? Only if the people wanted to eat it, they didn't want to have tar in their food, and that was produced microbiologically in food industry. No? Yeah, that's basically the truth. So there are two basic approaches to develop a target-orientated chemical reaction. And this is now very important. One of the approaches is to apply an intelligent, systematic trial and error process. This approach is mostly used in synthesizing artificial chemicals with a wide range of different plastics, be the most prominent example. Right? Because there, chemists more or less know about the certain reaction principles of organic chemistry. And then they go into their lab and they try to screw around with different inputs and different stoichiometric relations, different pH, different temperature, different pressures, different catalysts, and try to get that product they want to have. No? And by just trial and error, they found out it's a process. When they have the process, they invite the chemical engineers and they say, look what I've done in my laboratory, what wonders I have thought up, no? And now you do that in big. No? And this is how all this chemistry and chemical engineering work together in 90% of the chemical companies. The other approach is to copy and optimize processes occurring in nature. Also nothing new. All this basically done since many years in history, copying the nature in food industry, pharmaceutical industry. And this is also the very mostly used or almost exclusively used approach in environmental engineering. The later approach is widely used in environmental engineering. Also in the production of pharmaceutical and food products, processes in nature are copied and optimized with the scope of optimizing reaction efficiency, also the degree of how much you convert, and the volumetric turnover rate, which is mostly the case you look at, in order to reduce production costs. And environmentally engineering, mostly the approach is to pre-draw undesirable reactions in the environment under controlled reaction and technically optimized reactor plants. This is what we do in wastewater engineering. Okay. And I think, and this is a good point to close here, because then we start to get into the wastewater treatment plant. And so I'll leave you with thinking a little about what are the problems of wastewater to the environment. What do we pre-draw there? What and why and how? And it's 7 o'clock almost. In Germany, it's 5 o'clock here. Sorry. Good?
Yeah, I think it's a good stopping point.
Yeah. That's the way I look at it. Good.
'70s. It was the Clean Air and Water Act, signing that into law.
Yeah, excellent. In Iceland or?
No, in the U.S.
Oh, okay.
Did you find like
I just found some
oh wow.
it's a railroad.
Yeah.
Nice.
Twice, actually. And I'm hoping my girlfriend will help me edit it together into something that's sharp. My girlfriend is really good with video editing, whereas
Oh, okay.
I am not.
I'm not either. Unfortunately, we have one student who's good at it. He's a little, that's Tim Hofer, yeah, he's a little perfectionizer. We have a nice for flocculation for deaf, we have a nice video. Do you have access to that, Lisa? Zu dem Video, ja, den kennst du, ne? Den Tim gemacht hat. Flotation.
Yeah, I think I've got access. Is it in Studenten?
Hmm?
Is it in Studenten?
Yeah,
Yes.
I think. And then there's one which is also pretty nice. And it's done in his typical special manner from Michael Schubert. He's done on CAD.
Oh, I see. Yeah.
Hast du den mal? Der ist klasse, der hat den richtig gut
I
gemacht.
had the course with me.
Here?
Before you recorded, we had a course with him.
Yeah,
Drawing.
exactly.
Drawing.
Yeah, exactly. And you all liked it, and for that reason,
We all liked it.
yeah, you didn't.
Oh, I'm not so into drawing this stuff. But Micha is making it perfect. Really,
Yeah.
really good at it.
He didn't like it at all when he started. There was two students, no? They were pretty good in chemistry somehow, no? But no engineers at all, no? So when they had to make their somehow, no? They had no intention to, in mechanical engineering, as to how to produce welding and all this mechanical treatment of metal pieces, no? So when they came up to do their thesis, I said, I know what I'm going to do. I'm going to send you to my friend. He's a civil engineer, but he has his own M&E contractor firm, the one I told you about. And he's one of the best engineers I know. And he made those guys, and Michael Schubert is turned around 180%. He's only thinking a cat. He doesn't want anything anymore about chemistry. Almost a little bit too much, no? Because the combination makes it, of course. But he came up and he was trying to do the things quick and dirty. No? And they really, that's what they liked. So they trained him so much. That now he's over perfect almost. They made him draw every single fucking screw.
When I was in high school, I took a couple engineering classes, and it was all CAD, and like we had this one guy, like this one teacher was so anal retentive. I mean, he would make you draw every screw, it was great once you appreciated it. So you got to that point,
Well, I had students. I have a master's course. They can make it's like a project, no? And one of the project is to make 3 conveyors as a band conveyors, no? And for coal to a thermoelectrical plant. It's a little bit inspired by the it's a copy of the coal close of the coal transport from the harbor of Rostock to the coal to thermoelectrical plant. No? They have to reconstruct that. And one of the groups they made in one semester they handed in a CID file that you can run, and you can go into the motor, and even everything is turning. The band's running, the motor, everything is running. I don't know how this kid did that.
That's
okay. He has a job. He works this along, and is now. After that, he went back to that company where he is worked as a student, always in technical drawing. But he's so quick at